We're in.
Shall we play a game?
How about global thermonuclear war?
Hey there, Hacker Frogs. It's me, the Shy Hat, and we're doing HackerFrogs AfterSchool today. We're doing HackerFrogs free hack, and we're hacking all the things. So let's talk about what we're going to be covering on today's stream. NetDBG, hello, nice to see you here, and thank you very much to 3D Code Warrior and Waffler for chatting in Twitch chat before the stream started. Anyways, we're going to be doing 4 different topics on today's stream, as is per usual over here. And today is Friday, June 26, 2026. And the first topic we're going to be doing is we're going to be doing some puzzle games. Why do we do puzzle games? Because puzzle games are all about interacting with systems and finding interesting ways to interact with them. And that's what hackers do. Hackers have to learn how to interact with systems, sometimes very quickly, and figure out what they're all about. So that's why we're going to be playing some puzzle games to sharpen our problem-solving skills. That's the first topic. The second topic is going to be Hack the Box Intro Networking course. So we are going to be going through a introductory networking course. Computer networking is something that we deal with a lot on a daily basis, especially when you're doing technical cybersecurity / hacking roles. So that's what we're going to be doing in the second hour. We're going to be brushing up on some of our networking basics. The third topic we're going to be doing in the third hour is we're going to be doing HackerFrogs AfterSchool. HackerFrogs AfterSchool is a fun little program that I came up with to learn about a bunch of different topics across cybersecurity. This one is for network service hacking, and we're doing session number 3. Today we're going to be taking a look at how to enumerate web services on a network, and that's going to be the third hour of today's stream. The fourth hour and the fifth hour is going to be dedicated to a course over at CryptoHack, and that's called Public Key Cryptography. So I need to learn more about public key cryptography because I would like to teach more about it in the future. This is the RSA system, and we're going to be taking a look at the ins and outs of the RSA system as the last topic for today's stream. But without further ado, let's get into the first topic for today's stream, which is going to be some puzzle games over at Thinky Games. It's a very fun site, and it's got a lot of recommendation for intelligent games over there as well. Cypher says maybe you could put the times each topic will start so people know when to come back. Yeah, so usually each one of the topics, except for the last topic, is going to last about an hour. So if you want to come back for the Intro to Networking course, you come back in 60 minutes. If you want to come back for HackerFrogs AfterSchool, you want to come back in 120 minutes. And if you want to check out the Public Key Cryptography course, you would come back in 180 minutes. Maybe I could put down some rough times for when these things are going to start going forward. Thank you very much for the suggestion, Cypher. Thank you. Okay, let's get into our puzzle game topic over here. And we're doing, well, the last time we were here, we were trying to solve this puzzle here, number 23 of season 1. And you can find it here. You don't need to be logged in to do any of these puzzles. And here's what I want to do. I want to talk about how I learned to solve this puzzle, because it took me a while to get used to. So this is kind of like a Sudoku type of problem, but in this game, each one of these columns and rows has to have a star. And the stars can't be surrounded on either, they can't have any other adjacent stars. So there's a very interesting way of solving this challenge that I'll illustrate to you guys. So I'm by no means some sort of expert on these type of puzzles. It's just that I like to share the knowledge that I found out. Okay, so this is a game where you need to put a star on each one of these rows, and they can't have a star that is on either the same row or the same column as any other stars, and there also can't be any stars diagonally adjacent to them either. So each one of these stars has to be completely separate. Vic Thar, hello, nice to see you here. Welcome to the stream. So the way we want to start is we want to figure out where stars cannot be placed. especially if the stars are next to each other. So if there are two stars next to each other on this row, so they could be either here or here, these two, if the stars are on either of these spaces, then these two cells over here can't have stars. So with that, if we know that, we can also go to the second row, and in the second row, we've got two options. So its star could be here or here, and if the star is in either of these positions, then there can't be a star here, because there can't be a cell that is diagonally adjacent to any of these stars. Okay, and if we know that, then we know for sure that there is a star over here by process of elimination, because in this column, there's only one cell where there could possibly be a star. So that also means that we can block off all of these. And then from here, we know that there are two options in this column. And if there are two options in this column, here and here, then this cell can't be occupied. And then from there, we also know that there's only one option on this row for a star. So we can eliminate all of these cells. And with that done, in this column here, there could be a star here or here, which means that this cell cannot be occupied, which means there's only one choice for this column, and that rules out these cells, and that means that there is, let's see. Okay, @Val says, I got my MacBook Pro 2008 17-inch working. How? New charger. Yeah, it's always awesome when you're able to repurpose old equipment. That sounds really, really cool, @Val. Okay, so what else do we have? So there's now only one choice for this row over here, which means that this star occupies here, and then let's see, how does that help us determine other ones? So we got this one here, this one here. Okay. We can also do this one, because there's only one option for this row, and that means there's only one option for this row, which means we can eliminate that. And we only have this one left. We only have this star left to place. So that solves the challenge. Okay, so it is nice to be able to use logic to solve these puzzles. Let's move on to the next one. Okay, so this is the next level, number 24. And you know what? I just noticed that we don't have any music. We don't have any music on in the background. Let me go ahead and change and remedy that. Okay, we got our typical stream soundtrack over here. Ooh, that's a bit loud. Let's make it less loud. Okay, if you find that the music is too loud, let me know. Or if you find that the music is too soft, also let me know. Thank you. Okay, so this puzzle here, so it says an excited lockmaker greets her friend, eagerly sharing their new puzzle lock designs. No keys, more fun. Security, what's that? So what kind of puzzle do we have here? So this is a regular Sudoku puzzle. Okay, so this is a regular Sudoku. Let's make it a bit bigger. A variant of Sudoku that introduces unusually shaped regions. Fill in every cell in the grid from the numbers 1 to 6, making sure each number appears only once in each column, row, and region. Keep in mind that numbers can only appear once in the same row, numbers can appear only once in the same column, numbers can only appear once in the same region, and each region must contain the numbers 1 to 6. So we need to do some deduction to figure out where these numbers are going to go. Okay, let's make this puzzle as big as we can, and we'll start solving it. So I'm not especially good at doing Sudoku, but we'll try to work through this as best we can. So let's see, we got 1, 2, 3, 4, 5, 6 over here. We got so these two regions are already filled in, and so that means that this could be 2, 4, 6, 1. This can't be a 5. So this can't be a 5, so this must be... This can't be a 5 because there's already 1 in the same column here. So this is not a 5, but a 3. Because we're missing 3 in this row. So that means this must be the 5 over here. Okay, and then we've got 4, 5, 3, 6. We're missing the 1 and the 2 in this column. So I don't think we can solve this yet. All right, let's move around. So if you if you are better Sudoku players than I am, maybe you can shout out some hints as well. So let's see. We have a 3 and a 5 over here. I guess the easier... We want to look for a row where most of it is solved. 4, 3, and 4 over here. 1 and 2 over here. Maybe this column here. Although because this column is missing a 6. So one of these has to be a 6, and one of them has to be a 1. We're missing a 1 and a 6 over here. And then we've got... Maybe we can start getting some hints. Okay, let's read up on these hints. So the first hint is look for rows, columns, or regions that are already mostly full, and consider what numbers they still need. Okay? And now focus on the rightmost region and the second column. So the rightmost region is this one, and the second column is this one. Okay. Oh. And the third row seems like a good candidate to start from. The third row. So we've already done the third row here. Next up, that backwards F-shaped region. The backwards F-shaped region. So this one right here. Which numbers go in the 2 prongs of the backwards F? The 2 prongs of the backwards F. And does it help us complete the 4th column? You got this from here. Okay. So they say that look for... The third row seems like a good candidate. We've already filled this in. Now focus on the rightmost region in the second column. So the rightmost region is this one here. In the second column, the second column is this one. So there's 2 we need to fill in over here. So if we fill in the 2 over here, then we can also fill in the 2 over here. This column is missing a 1 and a 6, and this one is missing a 2. So 1, 6, 2, and 1, 6, 1, and 2. So, I mean, I guess we can start guessing a little bit and just kind of, because I'm not really too sure if we can do it purely by logic right about now. So if there's a 6 in this column, if there's a 6 in this column, then this has to be the 6, right? Because there's a 6 here, there has to be a 6 in this column as well. So that's the 6. So if this is the 6, then this has to be hell resistor. So 1 top, 2 down. 1 top, 2 down. Okay. Let me finish filling in this first over here. So 6, 4, 5, 3, and 1 and 2. So 1 and 2 have to go somewhere in here. 1 top, 2 down. So 1 top, are you talking about this? So this has to be a 1, and this has to be a 2. We can go with that, and then we can move over to here. So if a 2 is here, and we're missing a... So if this has a 1, then this has to be the 1 in this column, which means this is going to be the... This can't be the 6, though. Hold on. So this has to be the 6 here, and this has to be the 1 for this column. So this can't be the... So if neither of these work, this has to be the 2. This has to be the 2, and this has to be the 1. Because otherwise it doesn't work. It doesn't work here. So 1, 2, 3, 4, 5, 6 over here, and then they said something about the prongs in this column. So 1, 2, 3, 4, 5, 6, and then we've got 2 1s in this column. I think the 1 for... So this can't be a 1, and it can't be a 4. Can't be a 1, can't be a 4. We have a 5 here, we have a 5 here. We have a 5 here. Which numbers must go in the 2 prongs of the backwards F? We need to figure that out. So we got 6, 6. I mean, this could be 6. This can't be 5, it can't be 3. Can't be 5, can't be 3, can't be 1. Can't be 4. Actually, let's go back here. 1, 4, 3, 5, 6. So I think this should be 2. So if there's a 6 here, a 6 here, 2, 2, 2. Okay, and then there's only 2 more to solve here. We need a 3 and a 5. So this could be 3, this could be 5. 1, 2, 3, 4, 5, 6. And then from here we can try figuring out these ones. Because we need a 5 in this shape. Oh. The 5 can't be... The 5 has to go into one of these prongs, so this can't be... Okay, let's delete that. So one of these has to be the 5. Okay. So let's do... This is 5. And then this as... This is 2. 1, 2, 3, 5. But we already determined that this is... Maybe the 5 is here and the 6 is here. 1, 2, 3, 4, 5, 6. Then we've got... Six, 6, 6 here. This can't be 6 or 3 or 4. This might be 1. 1, 5. But if 2 over here is over here, that doesn't work. Man, I'm bad at this. Okay, let's just try. Let's restart, and we'll try again. Okay, so from here, 1, 2, 1, 2. Hey, St. Louis Phil. Hello, nice to see you here. We're struggling with puzzle games right now. Sudoku, in particular. So it's so we guess this is 3, because there's a 3 in this column. So this is either 3 or 1, 2, 3 or 5. Yeah. 3 or 5, so the 5 has to go in one place. So this can't be 5, so this has to be 3, because there's already a 5 in this column. So the 5 goes here, and the 3 goes here. So this is locked in. This is for sure. And then we need to figure out this column over here, the n column. And we need to use we need to use facts and logic to solve this. So there's already a 6 in here, so we can't put the 6 for this shape into this column. So this has to be the 6 over here. So that leaves a 1 and a 2 for these numbers here. Okay, and between 4 and 3. So if you guys want to give suggestions, so this is row 1, row 2, row 3, row 4, row 5, row 6, and this is column 1, column 2, column 3, column 4, column 5, and column 6. So this can't be... This can't be 5. No, what am I saying? This can't be 5. So this column is missing a 1 and a 2. So this is either 1 or 2. I wish we could... It's a good start. Yeah. It's okay. So the 1 and the 2... I wish we could know for sure. And then we've got this one as well, so this can't be 1. We're missing the 1 and the 6. We're missing the 1 and the 6, so this has to be the 6. Because we determined that there's a 6 up here, which means this has to be the 1. Oh man, I hate Sudoku. I mean, I'm not especially good at Sudoku either, but I'm trying to find a way. I'm trying to find a way to get better at all puzzle games, because puzzle games are all about figuring out a system, and it's fun to learn new systems. Or at least I like to tell myself that it's fun to learn new systems. Okay, Y6 on row 1. So Y6 on row 1. So row 1 here, we determined that this is the 6. Because there can't be another 6 on this column here, on the rightmost one. And there has to be a 6 inside this shape. So this has to be the 6 here, because it can't go in this column. So that lets us know that this has to be a 1, because there is a 6 in... Because there's a 1 and a 6 missing from column number 2. So the 6 has to go here, and the 1 has to go here. Hopefully that helps us determine the other numbers. Sudoku is one of those games where when you're not getting it, you feel really dumb, and, well... Let's see. But can it be 4 or 2? 4 or 2? You mean here? Can this be 4 or 2? Well, I mean, each one of these columns has to have a set from 1 to 6. And each one of these rows has to have a set from 1 to 6. And each one of these shapes that are outlined with the black lines has to have the numbers 1 to 6. So this has to be... Oh, okay. This helps us. So because there's a 1 in this row, this shape right here, this can't be the 1 because there's already a 1 in this row. So this has to be the 1, and this has to be the 2 over here. Yeah, that helps a lot. Okay, and now... No worries. We're here to learn. You can give this a try yourself, and if you're able to solve it before me, let us know. Because I bet most people can solve it before me, because I'm not very good at Sudoku. What column or row or shape has the least number to fill in now? Okay, so the hint told us that we were supposed to solve this one next. So these prongs over here, we got the 1. It can't be a 3, so can it be a 2? It could be a 2. It could be a 2, or it could be... So what's already here? So in these 2 prongs, there's 3, there's 4. I should probably write these down. There's a 3 and 4, there's a 5, a 3, a 4, and a 5 and a 1. So this could be 2 or 6. So either one of these spaces could be a 2 or a 6. Can you write a code program to figure out all the answers? I mean, we could. That's not really the goal of the game. The goal of the game is to get better at logic puzzles. So it's either a 2 or a 6. So there's a 6 here, there's a 6 here. There's already a 3. 2 or 6. I don't want to start guessing. This might be a 2, and if that's the 2, then this is the 6. Does this stand up to scrutiny? I don't know. So if we put the 2 here, this shape still needs a 1 and a 4 and a 5. A 1, a 4, and a 5. So the 5, this might be a 5. Or this is a 5. This is a 5 right here. Because there's a 5 in this column already, which means we can't put a 5 in this column. So why can't this be the 5? It's because there's already a 5 in this row. So this has to be the 5, and then we need to figure out what goes in this space. So there's a, it's not 1, it's not 5, it's not 3. It's not 1, it's not 5, it's not 3. That's where the 6 goes. Really? Let's lose time to make a bot to auto-solve all the Sudoku. Well, I mean, having the machine solve the Sudoku doesn't make the person better at solving the Sudoku. Okay. So could it be... Could this be 2 here? So 5 and a 2? Which means this column is missing a 1. Oh, no, wait. So, no, this has to be the 6. Because there can't be a 6 in this. So the 5 and the 6 go here. Because we've already placed 6 in this column and a 5 in this column. So those can't be present in these prongs over here. Yeah. That makes more sense. Okay, so what we're missing here is a 1, a 2, and a 4. So this can't be 4. This can't be 1. This can't be 1. This can't be 4. A 1, a 2, and a 4. Okay, 5 and 6 forced on column 4. Yeah, 5 and 6 are forced over here. Okay, so we're trying to figure out this row, or this column here. So column 5. So column 5... Column 5 can't have a 6, can't have a 5, can't have a 3. So it's 1, 2, 4. The 4 is not here. The 1's not here. One in row 2. So row 2 is at 1. Oh, you know what? Yeah, this has to be a 1. Because there's a 1 in this row, and there's a 1 in row 1 and there's a 1 in row 3. So these can't be 1s. So this has to be the 1. Yeah, Hill Resistor, that's correct. Great. Thank you. Thank you for that. Okay, and then we've got the 4 and the 2. So there's a 4 and a 2 in these spots. Although, I guess, because we put this 1 down, it might make it a lot easier to solve these ones over here as well. Okay, Rop M says 4 above 5. 4 above 5. So which 5 are we talking about? So this one? 4? Four, 2, then 4. 2. Column 5, 2, and then 4. So what's the logic here? So there's a 2 here. 4. 4. 4. Oh, okay. I see the 4. So, I mean, why are we not putting the 4 here then? Because in column 4 you already have a 4. So column 4, there's a 4. There's a 4 here. We need to fill out the shape. Okay, and then let's assume that this is correct. If we assume that this is correct, then we can go here and we can look for the 1, the 1 and the 4. So this has to be 4. No, this has to be 4, and this has to be 1. Because otherwise there's already occupied stuff, right? And then in this column, column 4, we're missing a 2 and a 3. So if we're missing a 2 and a 3 here, 3 has to go. Well, it doesn't have to go. There's a 2 and a 3. There's already a 2 here. So this has to be the 3. And this has to be the 2. Okay, let's see. Sorry, row 2, column 3 is the 2. Row 2, column 3, this is a 2. St. Louis Phil says I just beat it. Awesome, good job. Dylan Thomas is in column 3, then going down in the spaces left. Okay, let me just try to solve the rest of this, because there's not very many spaces left. And hopefully we got this right. I'm not completely sure. So what goes in? So this has 3 left. This is 2 left. So this row has 2 left. So we need a 1 and a 2. No. We need a 2 and a 6. So there's a 6 here, which means that this has to be the 6, and this has to be the 2. Okay, and if that's true, then in this column, we're missing a 4 and a 5. We're missing a 4 and a 5. So there's a 4 here already, so this has to be the 5, and this has to be the 4. Okay, and by process of elimination, that means that this is a 5, and this is a 3. You know what? I don't feel super good about how I solved that. I might have to come back later and redo this puzzle. But, I mean, we finished it. We'll move on to the next one. We've got 22 minutes left in this segment. Okay, so this one is an easy puzzle. Hopefully it doesn't take too long. Okay, the solver's sure the lockmaker can help. What about this new lock over here? Okay, here's the link for the new puzzle. Give it a try yourself. Okay, so what is this called? So this is a path variant of All or Nothing created by prolific puzzle designer Naoki Inaba in 2003. Trace a path from the entrance to the exit, which enters each region at most once. If it enters a region, it must visit every cell in that region. 2 regions connect vertically or horizontally. 2 regions connected vertically or horizontally cannot be left unvisited. Keep in mind that the path must visit all cells of each visited region. Ooh, that's loud. Okay, if 2 regions are next to each other, at least one of them must be visited. Not every region needs to be visited. Okay, so this is an important thing. We're not trying to cover every square. The path must not visit any regions more than once. Okay, we can't move into regions more than once. The path can never branch nor cross itself. Okay? And so this is supposed to be an easy one. We're trying to get from the entrance to the exit. And we need to visit every... Trace a path from the entrance to the exit. So the entrance is here, the exit is here. So we need to visit every cell in the region, and then we're going to cross into this region. We need to visit every cell in this region. And then we need to decide whether or not to visit this region or this region. So I think we need to cross every region over here, and then move down and visit every region in here, and then visit every cell in this region. I think that's all we need to do. Okay, that's done. Not super difficult. Okay, move on to the next puzzle. Alright, here is the next puzzle. So our hero peers over the cupboard door, from which sounds of discomfort can be heard. Has the lockmaker locked himself in? Okay, what kind of puzzle is this? Is this more Sudoku? This is more irregular Sudoku. Okay, so hopefully this one doesn't give us as many problems. So we've already done one of these today. Here is the link. This one seems a little bit more difficult than the one we were doing before. Okay, we need to do every row and column has 1, 2, 3, 4, 5, 6, and every one of these areas needs to have 1, 2, 3, 4, 5, 6. So I guess the place where we've got the most information is this this column right here, because we know that there's a 5 and a 6 here, so the 5 and the 6 can't go down in either of these spots. And we know that the 1 and the 2 are up here, which means the 1 and the 2 can't be in either of these spots, which means the... So 1, 2 go down here, and 5, 6 go up here. But what do we know for sure? So is this is the 2? Is this a 2? I don't know. we're missing 1, 2, 5, 6. So the 5 can't go here, right? And the 6 can't go here. There's a 2 and a 5. Ah, jeez. It looks, I mean, this seems like we don't have any information here. You know what? Let's get some hints. Let's get some hints because, you know, we've got the hints over here. We begin with only one of each number, so one of them must block off. One of them must block off enough cells in another region to let you place another number. Oh, okay, okay. So what are we missing? So 1, 2, 3, 4, 5, 6. Rob M says 6 in column 5. 6 in column 5 next to the 6. 6 here? Well, no. Column 5. This can't be a 6. So, I mean, why do you think this is, why do you think this is? Next to the 3. Next to the 3? So you think there's a 6 over here in column 5. So this is column 5 and this is column 6. There are 6 total columns and 6 total rows. So we begin with one of each number, so one of them must block off enough cells in another region. One of them must block off enough cells in another region for you to place another number. So 1, 2, 3, 4, 5, 6. Oh. 1, 2, 3, 4, 5. So the number 6 already exists in column 6. Yeah? The 6 already exists here. Oh yeah, okay. So there's a 6 here, and there's only one possible spot. But, I mean, why wouldn't the 6 be here or here or here? So this region, this area here is missing a 1, a 2, and a 1, a 2, and a 5, and a 6. Because of the region, okay. So this region is missing a 1, a 2, and a 5, and a 6. There's a 3, a 4. The shapes within the Sudoku also have to have 1 to 6. So this can't be a 1, a 2, a 5, and a 6. 1 and a 2 and a 5. So there's already a 5 here. So this could be 1. Okay, so this puzzle relies on a useful trick. Okay, let's learn the trick. If we know a few cells must have some sets of numbers, even if we can't place them, what does that tell us about other cells in the same row or column? So this column here this can't be a 4 or 5. This can't be a 4 or a 5. There can't be a 6 here. 4, 5, 6 cannot be in here. So this has to be 1 or 2 or 3. 1, 2, and 3 can't exist in this region over here. 1, 2, and 3 cannot. exist here. Well, I mean, it can't. I don't know. Man, these Sudoku puzzles really have me my brain hurting a bit. If we know a few cells must have a set of numbers, even if we can't place them, what does that tell us about other cells in the same row or column? And look at the top 3 cells in the rightmost column. Okay, so the rightmost column, top 3 cells. What numbers must they be? What does that tell you about the rest of the column? So the rightmost column is this one we're looking at here. The top 3 cells. So we got the 4, the 3, the 4, and the 6. The 3, the 4, and the 6 over here, so that it can't be... The 6 is also over here, so we can't... So this has to be 2, 5, and 1. 2, 5, 1. One to the right of 6. 1 to the right of 6 in column 6. This one. This has to be a 1. I mean... Yeah, I mean it could be 1, but... Why is this not... Why is this not 5? And why is this not 2? Okay, let's assume that this is correct. So this is a 6 and this is a 1. No worries. I think everybody's kind of confused. I'm not used to solving these Sudoku puzzles. Okay, so the top 3 cells in the rightmost column. Rightmost column, top 3 cells. What numbers must they be? So this is a 1, a 5, and a 2. I think I got what you meant by this has to be the 6 because this column can't have a 6 anymore. So if this is the 1, then this has to be the 2 and this has to be the 5. Okay, and then we can try to solve for down here. 1, 2, we're missing a 3 and a 4. So the 3 has to go here. No, the 3 has to go here because there's a 4 in this row already. So this has to be the 4. So 1, 2, 3, 4, 5, 6. And then we can start solving some other ones. Now, where do we go from here? Two, 2, 4, 5. Okay. So can we do the same trick anywhere else now? It might require a small extra step. So which region or which row or column has the has the most number of numbers filled in? So is it going to be something like this? Young Rome 7, thank you very much for following on Twitch. Thank you. Okay, so 1, 163. 163. We're missing 2 and 4 and 5. 2 and 4 and 5 over here in this row. 2 and 4 and 5. Two and 4 and 5. Okay. Rop says 4 at the base of column 2. Okay, so this is column 2. The base, we're assuming that this is what we're talking about. So this has to be 4. So you're saying that this has to be 4. I mean, there's a 4 here, a 4 here. Could it be anywhere else? Four, 4. My question is, why do you think that this is a 4? I mean, there's no 4 here already, of course. Why is this not a 3 or... No. Why is this not a 3 or a 2 or a 3 or a 2? Okay. Hell Resistor says row 2, column 5 is a 1. Row 2, column 5, this is a 1. I mean, we don't have a 1. It could be a 1, yeah? We've got 1s in these other rows. This can't be... Because you already have a 4 in column 4 and 5. 4 and 5. 4 and 5. There's a 4 here. I don't see the 4 in column 5. Horizontally. I mean, these are rows. These are columns. The columns go up and down, and the rows go left to right. Okay, Hell Resistor says that row 2, column 5 is a 1. Row 2, column 5, this is... So if you say this is a 1... I mean, it could be a 1, but why are we putting a 1 here? No worries, no worries. So the irregular, I mean, we need to take advantage of the irregular part of this irregular Sudoku. 1, 2. Okay, try the bottom row. What numbers must go in the leftmost cells? Okay, the bottom row is here. The leftmost cells have to be what? April, hello, nice to see you here. We're just solving some Sudoku, having a hard time of it. The link is over here if you want to give it a try. Okay, so there's no 3, 4, 6. So 3, 4, 6 is in this column here. So in this row, there can't be a 3, or 4, or 6. So this has to be 1. This can't be 1. This could be 2. This could be 2. And then there's a 5 here. This could be... This could be 5. I'm not completely sure. We're probably not going to solve this one before we move on to the next part of the stream. Okay, I'm sticking with 4 at the bottom row of column 2 because the numbers can only appear once in each row. Okay, so 1, 2. I mean, if that's the case, then this has to be 3, right? And then it makes it a lot easier for us to try to figure out what these 2 cells are supposed to be, because we're missing our 3 and we're missing our 4. Okay, well. We're missing our 3 and we're missing our 4. But this is definitely wrong then. Because we got the 3 and the 4 in... We can't put either of them in here. So maybe this is the 2? And this is the 1? No, but that can't be the 1. Yeah, we're oh boy. Okay, I think we're not we're not going to be able to solve this one. But if you can solve it, then please please let us know. We're going to move on to the next topic. I guess we got stumped. All right, I'm going to after the stream is over, I'm going to try to figure out what the logic is behind puzzles like this. I need to learn more Sudoku tricks. But let's go ahead and move on to the next topic for today's stream, which is networking stuff. Computer networking, something that is a little bit less confusing to me. We might come back to this if we've got some extra time, but let's go ahead and do the Try Hack Me course. Sorry, the Hack the Box course. So, if you have an account over at Hack the Box, you can take a look at the course over here. We're going to be spending the next 60 minutes talking about this. Okay, so the name of the course is Network Foundations. And we're talking about components of a computer network. Sure. Make it a little smaller. Okay, so we continue in our journey into InfoSec, understanding the components that comprise a network. This is essential. We know that currently devices are able to communicate with each other, share resources, and access the internet with an almost uniform consistency. What exactly facilitates this? The primary components of the network include our end devices. So the end devices are computers, smartphones, tablets, IoT, smart devices over here. Our intermediary devices are switches, routers, modems, and access points. Our network media and software components are cables, protocols, management, and firewall software. And their servers are web servers, file servers, mail servers, and database servers. So I solved the Sudoku, took me 16 minutes and 10 seconds. Awesome, St. Louisville. Thank you very much for the effort. Okay, so let's talk about each one of these devices in detail. So end devices. An end device, also known as a host, is any device that ultimately ends up sending or receiving data within a network. Personal computers and smart devices, such as phones and smart TVs, are common end devices. Users routinely interact with them directly to perform tasks like browsing the web, sending messages, and creating documents. In most networks, such devices play a crucial role in both data generation and data consumption. Like when users stream videos or read web content, end devices serve as the primary user interface to the World Wide Web, enabling users to access network resources and services seamlessly. Through both wired Ethernet and wireless Wi-Fi connections. Another typical example of this would be a student using a notebook to connect to a school's Wi-Fi network, allowing them to access online learning material, submit assignments, and communicate with instructors. Okay, intermediary devices. So these have the unique role of facilitating the flow of data between end devices, either within a local area network or between different networks. These devices include routers, switches, modems, and access points, all of which play crucial roles in ensuring efficient and secure data transmission. Intermediary devices are responsible for packet forwarding, directing data packets to their destinations by reading network address information and determining the most efficient paths. They connect networks and control traffic to ensure enhanced performance and reliability. By managing data flow with protocols, they ensure smooth transmission and prevent congestion. Additionally, intermediary devices often incorporate security features like firewalls to protect certain networks from unauthorized access and potential threats. Operating at different layers of the OSI model, for example, routers at the network layer, layer 3, and switches at the data link layer, layer 2, they use routing tables and protocols to make informed decisions about data forwarding. A common example is a home network where intermediary devices like routers and switches connect all household devices, including notebooks, smartphones, and smart TVs, to the internet, enabling communication and access to online resources. Okay, and we're talking about network interface cards, or otherwise known as NICs. A network interface card is a hardware component installed in a computer or other device that enables connection to a network. It provides the physical interface between the device and network media, handling the sending and receiving of data over the network. Each NIC has a unique MAC or media access control address, which is essential for devices to identify each other and facilitate communication at the data link layer. NICs can be designed for wired connections such as Ethernet cards that connect via cables, or wireless connections like Wi-Fi adapters utilizing radio waves. For example, a desktop computer might use a wired NIC along with an Ethernet cable to connect to a local network, while a laptop uses a wireless NIC to receive and connect to Wi-Fi. Okay, we also have routers. A router is an intermediary device that plays a hugely important role, the forwarding of data packets between networks and ultimately directing internet traffic. Operating at the network layer 3 of the OSI model, routers read the network address information and data packets to determine their destinations. They use routing tables and routing protocols such as Open Shortest Path First (OSPF) or Border Gateway Protocol (BGP) to find the most efficient path for data to travel across interconnected networks, including the internet. They fulfill this role by examining incoming data packets and forwarding them towards their destinations based on IP addresses. By connecting multiple networks, routers enable devices on different networks to communicate. They also manage network traffic by selecting optimal paths for data transmission, which helps prevent congestion, a process known as traffic management. Additionally, routers enhance security by incorporating features like firewalls and access control lists, protecting the network from unauthorized access and potential threats. For example, in a home network, a router connects all household devices, such as computers, smartphones, and smart TVs, to the internet provided by an internet service provider, otherwise known as an ISP. The router directs incoming and outgoing internet traffic efficiently, ensuring that each device can communicate with external networks and with each other. We also have switches. The switch is another integral component, with its primary job being to connect multiple devices within the same network, typically a local area network or a LAN. Operating at the data link layer, layer 2 of the OSI model, switches use MAC addresses to forward data only to the intended recipient. By managing data traffic between connected devices, switches reduce network congestion and improve overall performance. They enable devices like computers, printers, and servers to communicate directly with each other within the network. For instance, in a corporate office, switches connect employees' computers, allowing for quick file sharing and access to shared resources like printers and servers. Okay, and we also have hubs. A hub is a basic and now antiquated networking device. It connects multiple devices in a network segment and broadcasts incoming data to all connected ports, regardless of the destination. Operating at the physical layer, layer 1 of the OSI model, hubs are simpler than switches and do not manage traffic intelligently. This indiscriminate data broadcasting can lead to network inefficiencies and collisions, making hubs less suitable for modern networks. For example, in a small home network set up from earlier times, a hub might connect a few computers, but today switches are preferred due to better performance and efficiency. Dapel says hubs were the best at LAN parties. I didn't participate in that many LAN parties, but I'll take your word for it, Dapel. Okay, network media and software components. Network media and software components are vital elements that enable seamless communication and operation within a network. Network media such as cables and wireless signals provide the physical pathways that connect devices and allow data to be transmitted between them. This includes wired media like Ethernet cables and fiber optic cables, which offer high-speed connections, as well as wireless media like Wi-Fi and Bluetooth, which provide mobility and flexibility. On the other hand, software components like network protocols and management software define the rules and procedures for data transmission, ensuring that information is correctly formatted, addressed, transmitted, routed, and received. Network protocols such as TCP/IP, HTTP, and FTP enable devices to communicate over the network, while network management software allows administrators to monitor network performance, configure devices, and enhance security through tools like software firewalls. Okay, we also have some cabling and connectors. So these are the physical materials used to link devices within a network, forming the pathways through which data is transmitted. This includes various types of cables mentioned previously, but also connectors like the RJ45 plug, which is used to interface cables with network devices such as computers, switches, and routers. The quality and type of cabling and connectors can affect network performance, reliability, and speed. For example, in an office setting, Ethernet cables with RJ45 connectors might connect desktop computers to network switches, enabling high-speed data transfer across the local area network. Network protocols. So these are sets of rules and conventions that control how data is formatted, transmitted, received, and interpreted across a network. They ensure that devices from different manufacturers and with varying configurations can adhere to the same standard and communicate efficiently. Protocols encompass a wide range of aspects such as data segmentation, addressing, routing, error checking, and synchronization. Common network protocols include TCP/IP, which is ubiquitous across all internet communications, HTTP and HTTPS, which is the standard for web traffic, FTP for file transfers, and SMTP for email transmissions. For instance, when we browse a website, the HTTP or HTTPS protocol dictates how our browser communicates with the web server to request and receive web pages, ensuring that the data is correctly formatted and securely transmitted. Network management software consists of tools and applications used to monitor, control, and maintain network components and operations. These software solutions provide functionalities for performance monitoring, configuration management, fault analysis, and security management. They help network administrators ensure that the network operates efficiently, remains secure, and can quickly address any issues that arise. For example, in a corporate environment, the IT department might use network management software to oversee all devices connected to the company network, monitor traffic for unusual activity, update device configurations remotely, and enforce security policies, maintaining optimal network performance and security. Software firewalls. So these are security applications installed on individual computers or devices that monitor and control incoming and outgoing network traffic based on predetermined security rules. Thatch, oh, hello, nice to see you here. What is up? Unlike hardware firewalls that protect entire networks, software firewalls, also called host-based firewalls, provide protection at the device level, guarding against threats that may bypass the network perimeter defenses. They help prevent unauthorized access, reject incoming packets that contain suspicious or malicious data, and can be configured to restrict access to certain applications or devices, or services, rather. For example, most operating systems include a built-in software firewall that can be set up to block incoming connections from untrusted sources, ensuring that only legitimate network traffic reaches the device. Okay, so what do we have? The Linux-based software firewall IP tables being used to drop incoming ICMP traffic. So let's see. So we see we're trying to use the ping command to access a certain device. Okay, and then they send a rule to IP tables to not respond to ICMP traffic. They run the ping command again, and now all their ping packets are dropped. Okay. Servers. A server is a powerful computer designed to provide services to other computers known as clients over a network. Servers are the backbone behind websites, email, files, and applications. In the realm of computer networking, servers play a crucial role by hosting services that clients access, such as web pages and email services, facilitating service provision. They enable resource sharing by allowing multiple users to access resources like files and printers. Servers also handle data management by storing and managing data centrally, which simplifies backup processes and enhances security management. Additionally, they manage authentication by controlling user access and permissions across multiple components in the network. Servers often run specialized operating systems optimized for handling multiple simultaneous requests in what is known as the client-server model, where the server waits for requests from clients and responds accordingly. Whether you know it or not, this is what was happening under the hood the last time you accessed a website from your notebook. Your browser sends a request to the web server hosting the site, and the server subsequently processes the request and sends back the web page data in its response. Conclusion. As we have seen, the technology stack needed for worldwide computer networking requires multiple components. End devices are the user's primary interface with the network. Intermediary devices manage data traffic and connectivity, and servers provide resources and services. Together they enable the seamless flow of information that powers modern communication. Okay, so we need to answer some questions now. So question 1. What type of network cable is used to transmit data over long distances with minimal signal loss? Okay, so people who are computer networking people can probably answer these questions. So what kind of network cable is used to transmit data over long distances? So long distances with minimal signal loss. So are we talking about Ethernet cables? Nope, they're not looking for Ethernet cables. Fiber optic cables. That's a good answer, April. Fiber optic. Okay, that was correct. Question 2. What protocol manages data routing and delivery across networks? Which protocol manages data routing and delivery across networks? So we're probably talking about the TCP/IP protocol or the IP protocol, right? Okay, we're probably timing out on this one. The border gateway protocol. Data routing and delivery. Okay, so if we were to look for routing, and we're looking for a protocol that does routing. So let's see, Dapril offered up Border Gateway Protocol. So they use routing tables and routing protocols such as the open shortest path first. Okay, we got two protocols here. And we got the Border Gateway Protocol to find the most efficient path for data to travel across interconnected networks, including the internet. So this is a routing protocol, so Border Gateway Protocol. Okay, and we'll move down to the question. Thank you, April. No, maybe they're looking for the acronym BGP. Which protocol manages data routing? Border Gateway Protocol. Well, I mean, there was one other protocol that was mentioned there as well. So it was the shortest something something, shortest path first. Open shortest path first. Open shortest path first. We'll try that one. And see if that's what they're looking for. Okay, so we're looking for a protocol that manages data routing and delivery. Delivery? So we're looking for a protocol. Sometimes... Okay, so network protocols... they might be talking about the TCP/IP protocol. Yeah, we'll give it a try. That's what they're looking for. They were looking for TCP/IP. Okay, next question. What software is used to oversee and administer network operations? What software is used to oversee and administer network operations? So that would be... It is ubiquitous. That's true. What software is used to oversee and administer network operations? Some sort of management software. Management. That's not how you spell it. Manage. So we're looking for something that's 3 network management software. I mean, that's probably what we're looking for, right? Okay, next question. What software is used to protect individual devices from unauthorized network access? One word. So we're looking for like a firewall, right? Protect individual devices from unauthorized network access. So that's like a host firewall? Looks like that's not the answer I was looking for. Okay, so what software is used to protect individual devices from unauthorized network access? Well, I'm pretty sure we're looking for the word firewall. And I'm pretty sure that this answer is going to time out. We're talking about it. So what software is used to protect individual devices from unauthorized network access. Okay, let's go back up. SpongeBob, hello, nice to see you here. What is up with you? Okay, it's not going to be servers. So what's a piece of software that can prevent... Am I misspelling the word firewall? Can't be it, right? Okay, so the answer, the question is, what software is used to protect individual devices from unauthorized network access? We're looking for a one-word answer. I mean, I thought that the answer would be firewall. That is the answer. Why didn't it accept it the first time? Sometimes, Anyways, question number 5. What type of cable is used to connect components within a local area network for high-speed data transfer? So this is, they're probably looking for Ethernet in this case. It's just firewall. Ethernet, yeah, I mean, my guess is Ethernet, but I don't know if they're going to accept this. Anyway, so we've got an ad running on Twitch right now, so when ads run on Twitch, we also put on the birds. Whoa, that's a bit loud. Let's make it less loud. Okay, and we'll be back in about 30 seconds. I just need to have a little bit of water. Okay, and so they're not looking for... So we tried Ethernet. Let's try it one more time. That was the correct answer. For some reason, sometimes you need to put in the correct answer more than once. Question 6. What device connects multiple networks and manages data traffic to optimize performance? Connects multiple networks and manages data traffic. So I think we're talking about either a router or a switch. What device connects multiple? I think the router is the one that connects multiple networks. Yeah, okay. All right, let's move on to the next section. Okay, now we're doing network communication. So for a network to function and facilitate communication properly, there are 3 crucial components: MAC addresses, IP addresses, and ports. Together, these elements ensure that data is correctly sent and received between devices across both local and global networks, forming the backbone of seamless network communication. So MAC addresses, IP addresses, and ports. So what are MAC addresses? Media access control addresses are unique identifiers assigned to a network interface card, or a NIC, of a device, allowing it to be recognized in a local network. Operating at the data link layer, layer 2 of the OSI model, the MAC address is crucial for communication within a local network segment, ensuring that data reaches the correct physical device. Each MAC address is 48 bits long and is typically represented in hexadecimal format, appearing as 6 pairs of hexadecimal digits separated by colons or hyphens. So for example, something that looks like this. The uniqueness of a MAC address comes from its structure. The first 24 bits represent the organizationally unique identifier, OUI, assigned to the manufacturer, while the remaining 24 bits are specific to the individual device. This design ensures that every MAC address is globally unique, allowing devices worldwide to communicate without address conflicts. So the first 24 bits, so this is 8 bits. So this represents 16 bits. So the 2 hexadecimal digits can represent 16 bits. So that's 32, and that's 48. No. First 24 bits. First 24 bits. So I'm assuming that this is split in half. So if we got 1, 2, 3, 4, 5, 6. So this would represent 24 bits, and this would represent 24 bits. Okay, the Windows getMAC command will return the MAC address of every network interface card on the host. GetMAC. GetMAC. I mean, you can also run like a similar command in Linux to get information about physical devices. It's the IP command, right? So IPA also gets you MAC addresses. Yeah. So these are the MAC addresses for the different for the different interfaces. Okay. How MAC addresses are used in network communication. MAC addresses are fundamental for local communication within a local area network, as they are used to deliver data frames to the correct physical device. When a device sends data, it encapsulates the information in a frame containing the destination MAC address. Network switches then use this address to forward the frame to the appropriate port. Additionally, the Address Resolution Protocol, or ARP, plays a crucial role in mapping IP addresses to MAC addresses, allowing devices to find the MAC address associated with the known IP address within the same network. This mapping is bridging the gap between logical IP addressing and physical hardware addressing within the LAN. Imagine two computers, computer A with an IP address of this, which we will discuss shortly, and computer B, which has another IP address, connected to the same network switch. Computer A has the MAC address this one, while computer B's MAC address is this other one. When computer A wants to send data to computer B, it first uses the Address Resolution Protocol, ARP, to discover computer B's MAC address associated with its IP address. After obtaining this information, computer A sends a data frame with the destination MAC address set to computer B's MAC address. The switch receives this frame and forwards it to the specific port where computer B is connected, ensuring that the data reaches the correct device. This is illustrated in the following diagram. Okay, I think we can make this diagram bigger. Okay, let's make it as big as possible. So we've got a few different few different hosts here. So this is the .1 device, the .3 device, the .5 device, and the .4 device over here. Okay, so let's see. Requesting the MAC address from the 5 device going this way. So it goes to the router, and then the router forwards it to the correct IP address, and then this host sends back the MAC address to the router, which sends it back to the original request, the original requester over here. Okay. IP addresses. What is an IP address? In Internet Protocol, IP address is a numerical label assigned to each device connected to a network that utilizes the Internet Protocol for communication. Functioning at the network layer or layer 3 of the OSI model, IP addresses enable devices to locate and communicate with each other across various networks. There are 2 versions of IP addresses. There's IPv4 and IPv6. IPv4 addresses consist of a 32-bit address space, typically formatted as 4 decimal numbers separated by dots, such as 192.168.1.1. In contrast, IPv6 addresses, which were developed to address the depletion of IPv4 addresses, have a 120-bit address space and are formatted in 8 groups of 4 hexadecimal digits. For example, this thing over here. How IP addresses are used in network communication. Routers use IP addresses to determine the optimal path for data to reach its intended destination across interconnected networks. Unlike MAC addresses, which are permanently tied to the device's network interface card, IP addresses are more flexible. They can change and are assigned based on the network topology and policies. A communication example between two devices on the same network can be similarly illustrated as shown previously in the MAC address subsection. Okay, so this is also an example of different IP addresses on the same network. Ports. So a port is a number assigned to specific processes or services on a network to help computers sort and direct network traffic correctly. Snollygoster, TCP/IP, TCP/IP. Yep, we're talking about that. We're talking about all sorts of fun networking topics. So ports function at the transport layer, or layer 4 of the OSI model, and work with protocols such as TCP/IP and UDP. TCP and UDP, rather. Ports facilitate the simultaneous operation of multiple network services on a single IP address by differentiating traffic intended for different applications. When a client application initiates a connection, it specifies the destination port number corresponding to the desired service. Client applications are those that request data or services, while service applications respond to those requests and provide the data or services. The operating system that directs the incoming traffic to the correct applications based on this port number. Consider a simple example where a user accesses a website. The user's browser initiates a connection to the server's IP address on port 80, which is designated for HTTP. The server listening on this port responds to the request. If the user needs to access a secure site, the browser instead connects to port 443, the standard for HTTPS. Ensuring secure communication, port numbers range from 0 to 65,535 and is divided into 3 main categories, each serving a specific function. Okay, so we can use the netstat tool to view active connections and listening ports. So, we can also do the same kind of thing over on our own system. So we run netstat 2lpn, and this lets us know that there are these ports and services listening on our devices over here. Well, not the services. They know that these are ports that are listening on our device. So we got this one on 39,000 something something, and this other one on 48,000. Okay, we've got well-known ports. So well-known ports are ports 0 to 1023. They're reserved for common and universally recognized services and protocols, as standardized and managed by the Internet Assigned Numbers Authority, or IANA. For example, HTTP, which is the foundation of data communication for the World Wide Web, uses port 80, although browsers typically do not display this port number to simplify user experience. Similarly, HTTPS uses port 443 for secure communications over networks, and this port is generally not displayed by browsers. Another example is FTP, which facilitates file transfers between clients and servers using ports 20 and 21. So there's this group, which is 0 to 1023. The next set is registered ports, which are ports 1024 to 49,151. Registered ports are not as strictly regulated as well-known ports, but are still registered and assigned to specific services by the IANA. These ports are commonly used for external services that users might install on a device. For example, many database services, such as Microsoft SQL Server, use port 1433. Software companies frequently register a port for their applications to ensure that their software consistently uses the same port on any system. This registration helps in managing network traffic and prevents port conflicts across different applications. And then we've got our high number ports, also known as dynamic and private ports, which are from 49,000 to 65,000. These numbers over here. So these are known as ephemeral ports. They're typically used by client applications to send and receive data from servers, such as when a web browser connects to a server on the internet. These ports are called dynamic because they are not fixed. Rather, they are randomly selected by the client's operating system as needed for each session. Generally used for temporary communication sessions, these ports are closed once the interaction ends. Additionally, dynamic ports can be assigned to custom server applications, often those handling short-term connections. Okay, what do we got here? Browsing the internet example. The following example represents the steps taken for a web request to reach the correct destination and return the information we seek. So step 1, DNS lookup. Our computer resolves the domain name to an IP address. So for example, this IP address for example.com. I wonder if this IP address is actually example.com. Well, I mean, these things kind of change all the time. So one is DNS lookup, and then there's data encapsulation. So your browser generates an HTTP request. The request is encapsulated with TCP, specifying the destination port, either 80 or 443. The packet includes the destination IP address, which is the one for example.com. On the local network, our computer uses ARP to find the MAC address of the default gateway, or the router. Step 3 is data transmission. The data frame is sent to the router's MAC address. The router forwards the packet towards the destination IP address, and then the intermediate routers continue forwarding the packet based on the IP address. Step 4 is server processing. The server receives the packet and directs it to the application listening on port 80 or 443. The server processes the HTTP request and sends back a response following the same path in reverse. Step 5. Response transmission. The server sends the response back to the client's temporary port, which was randomly selected by the client's operating system at the start of the session. The response follows the reverse path back through the network, being directed from router to router based on the source IP address and the port information until it reaches the client. Okay, so I guess we're going to answer some questions now. Okay, so the first question is, which protocol maps IP addresses to MAC addresses? IP addresses to MAC addresses, there's a specific protocol that does this. It starts with the number, well, it starts with the letter A. So this is the address resolution protocol, otherwise known as ARP. Sorry, does it have a dash in here? Okay, let me... Address Resolution Protocol, ARP. Let's try that again. Okay, submit. Am I totally off base on this. What protocol maps IP addresses to MAC addresses? I thought it was the Address Resolution Protocol, or ARP. It was ARP. Sometimes I get the feeling that I feel really dumb when I answer these questions because it doesn't accept the right answer right away. Okay, which IP version uses 128 bits for addressing? 128 bits for addressing, so that's probably the IPv6. IPv6, which is the one with all the octet, with all the hexadecimal digits. Okay. Question 3. At which layer of the OSI model do ports operate? So I'm pretty sure that this... Yeah, IPv6 was the answer, yeah. At which layer of the OSI model do ports operate? So let's see. So I think they operate at layer 4. Let me see if I can remember what layer 4 is. So all people seem to need data processing. All people seem to need data processing. So it's like A is for application, P is for presentation, S is for session. So these go in reverse. So this is actually layer 7. Layer 7, layer 6, layer 5, layer 4, layer 3, layer 2, and layer 1. So P layer 1 is physical. D is data link. Session or transport. Oh, the transport layer. Transport. The network. This is the network layer. So we should be dealing with the transport layer, which is layer 4 for networking ports. Transport layer. Okay, that was correct. What is the designated port for HTTP? So HTTP, which is unencrypted web pages, it operates by default on port 80. Question 5. What is the first step in the process of a web browsing session? What is the first step? So this is not something I know offhand. We'll just go back to the example. DNS lookup. So DNS lookup is the first step for a web request. DNS lookup. Okay. And we can move on to the next section. This is probably going to be the last section for today. Oh, DHCP. Okay. Alright. Annoying, they are so picky about input and don't get why I'm wrong. Yeah, I mean, sometimes you get stuck on specific questions in Hack the Box Academy, and then you can't progress, and you can't get your cubes back, because you're not answering the questions correctly. I don't know. Sometimes I have kind of like unpleasant experiences with Hack the Box Academy. Dynamic Host Configuration Protocol. So this is DHCP. So this is basically the protocol that assigns IP addresses to devices on your network. So introduction to DHCP. In a computer network, every device needs a unique IP address to communicate with other devices. Manually assigning IP addresses to each device can be time-consuming and can cause errors, especially in large networks. To resolve this issue, networks can rely on the Dynamic Host Configuration Protocol, or DHCP. So this is a network management protocol used to automate the process of configuring devices on IP networks. It allows devices to automatically receive an IP address and other network configuration parameters such as subnet mask, default gateways, and DNS servers, without manual intervention. DHCP simplifies network management by automatically assigning IP addresses, significantly reducing the administrative workload. The automation ensures that each device connected to the network receives a unique IP address, preventing conflicts and duplication of addresses. Furthermore, DHCP recycles IP addresses that are no longer in use when devices disconnect from the network, optimizing the available address pool. How DHCP works. DHCP process involves a series of interactions between the client, the device requesting an IP address, and the DHCP server, the server running on a network device that assigns IP addresses. This process is often referred to as DORA, an acronym for Discover, Offer, Request, and Acknowledge. Below we can see the breakdown of DORA. Before we explore the DORA steps in detail, let's first clarify the roles of the DHCP server and the DHCP client. Okay, so the server is a network device, like a router or a dedicated server, that manages IP addresses allocation. It maintains a pool of available IP addresses and configuration parameters. The client is any device that connects to the network and requests network configuration parameters from the DHCP server. Hello, Shota, nice to see you here. How are you doing? Hope you're having a good Friday. Below, we break down each step in the DORA process. So, Discover. When a device connects to the network, it broadcasts a DHCP Discover message to find available DHCP servers. Offer. DHCP servers on the network receive the Discover message and respond with a DHCP Offer message, proposing an IP address lease to the client. Request. The client receives the offer and replies with the DHCP request message, indicating that it accepts the offered IP address. Acknowledge. The DHCP server sends a DHCP acknowledge message confirming that the client has been assigned the IP address. The client can now use the IP address to communicate on the network. Okay? So a Linux host connected to a wireless network initializes the DORA process. So we can see here in... Can we pause this? No, we can't pause this. Okay. But this, I guess this is illustrating a device getting an IP address. So the IP address assignment via DHCP is not permanent, but is instead issued with a specific lease, a lease time. For instance, a DHCP server might assign an IP address to a smartphone with a lease time of 24 hours. After this period, the smartphone must request a renewal of the lease to continue using the IP address. Regarding the renewal process, before the lease expires, the client must proactively attempt to renew its IP address lease. This involves sending a renewal request to the DHCP server. As the lease nears its expiration, the client communicates with the DHCP server, asking if it can continue using the assigned IP address, to which the server can respond affirmatively, extending the lease. Okay, so... Okay, Shota says, I'm good, but 2 typhoons are hitting Japan and earthquakes. I'm sorry to hear that. I haven't heard very much news about it, but it is typhoon season. Summer is kind of like the typhoon season for Japan, isn't it? I don't know about an earthquake season, but I'm pretty sure that summertime is typhoon season for some parts of Japan. Example scenario. Let's walk through a simple example based on the steps previously discussed on how DHCP assigns an IP address to a device. Alice brings her new laptop to the office and connects it to the network. Since the laptop doesn't have an IP address yet, it sends out a DHCP Discover message to find a DHCP server. The office's DHCP server receives the message and responds with an offer, proposing the IP address, this one over here. Alice's laptop receives the offer and sends back a DHCP request message to accept the IP address. Finally, the DHCP server acknowledges this request and confirms the assignment. The laptop is now configured with the IP address, this address, allowing it to communicate on the network. Shota says, yes, the season is often happening. Typhoon season. I think earthquakes can also cause typhoons. I'm not sure about the relationship between earthquakes and typhoons. Okay, so the IP address, this one, assigned to Alice's laptop is not permanent, but is instead provided for a specific duration known as a lease time. As this lease nears expiration, Alice's laptop must renew it to continue using the IP address. To do this, it sends another DHCP request to the DHCP server asking to extend the lease. If the server can renew the lease, it will respond with a DHCP acknowledge message confirming the continued use of the IP address. Oh yeah, no. Earthquakes do cause tsunami, yeah. Tsunamis are basically earthquakes that move ocean waves. Yeah. Okay, and here's a lovely diagram that talks about this. Alright, let's answer the questions. Which protocol automates IP address configuration for devices in the network? So we were just talking about this all this time. DHCP. So Dynamic Host Configuration Protocol, I think it stands for. Okay, next question. Yeah, tsunami are caused by earthquakes. Which acronym describes the sequence of messages exchanged during the DHCP process? So this was the, I'm not exactly, let's think about this. So that's, it was the DORA process. Dora, I guess we could call it the flow. So D stands for D, O, R, and A. So R stands for response, I'm pretty sure, and A stands for accept. O stands for offer. And what did the D stand for again? Offer. Discover. So discover, offer, response, and accept. So DORA. Okay. Question 3. What kind of message does a client send to accept an IP address from a DHCP server? So this is the response. Is it not response? Is it receive? I could have sworn this was response. Response. I need to spell everything correctly. Response. Let me look this up. Request. It actually stands for request. Darn. And A stands for acknowledge, not accept. Okay. So this is receive, and this is acknowledge. Okay, let's go back down. Wait, what was it again? Receive. I feel like am I going crazy? Receive, right? No. Hold on. Oh no. Man, I need to... take better notes. Okay, so... request. So sometimes you'll send the correct answer, and it'll still say that it's not the correct answer. Probably because the traffic didn't go through properly. Okay, it says it's incorrect. We'll submit again. Request. And it wanted, I guess it wanted it with the capital letter. Okay, so network address translation. So NAT. So I don't think we have got enough time. Is it worth studying this if you forget the next time? Is it worth studying this if you forget the next time? I mean, I'm pretty sure in a lot of circumstances you're not going to be expected to know the exact 4 steps that are used for DHCP, but it is good to familiarize yourself with this so that, you know, when you encounter it, it's not foreign to you. So you'll take a networking course, and then you will forget some information over time, but it's good to refresh yourself every once in a while. But yeah, the module we're doing is this one over here, and it's essentially free. And if you've never taken a computer networking course before, it's got a lot of good information that you're going to encounter over and over again while you're doing technical computer technology stuff in general, and cybersecurity stuff in particular. Anyways, let's go ahead and start the next part of the stream. No one can remember this all at once. I mean, the other thing is that if you're not actively using the knowledge, you'll forget it over time. So this is another reason why you want to take good notes. I'm not especially taking notes while I'm working through this, but if you take good notes, you're able to reference stuff rather quickly. The other thing is that a lot of this stuff you can also just quickly look up on the internet, but you don't have the internet available to you at all times. Anyways, let's move on to the next part of today's stream. Okay, so we're going to be talking about network service hacking over here. Let me change my overlays and then we can get started. I wouldn't say no one, I'm sure. Well, I mean, there are people, there are experts out there on every subject, basically, if you look hard enough. Okay, we're done with topic 2. Topic 3 is here, and topic 4 is on deck. Alright, so this is our educational part. Well, I mean, you know, all parts of the stream are educational parts in the stream, but this is where I teach people about network service hacking. So this is HackerFrogs AfterSchool. This is the network service hacking course. This is session number 3. Okay, so this is the 3rd session for network hacking. We're going to go over the concept we covered in the previous session. So Network Chuck is good for networking. I agree. He's got a very, very, very popular YouTube channel. Red Sly Fox, nice to see you here, by the way. Okay, so in the previous class we talked about three common network protocols and how to interact with them. So the FTP service, which is the file transfer protocol, this is a common networking service which allows users to upload and download files. So pretty similar to the FTP protocol is the SMB service, which is server message block. So this is a file and printer sharing service that is most commonly associated with the Windows OS. too much coffee. Network chuck, too much coffee? Maybe. And the telnet service. So telnet is a service that allows remote terminal login, and it's the predecessor to the SSH service. So this is basically a service you use to do remote login to servers. So in this session, we're going to be talking about web service enumeration. We're going to be talking about a few different tools we can use to do web service enumeration, such as the derb tool, the nicto tool, and the GoBuster tool. We'll be talking about what these are in just a sec. So why are we learning web stuff? So this is a network hacking course, so why are we learning how to enumerate web servers? The reason is because web services are network services. In fact, web services are among the most popular networking services. So we're learning how to hack network services, and web servers are some of the most popular network ones. So we're going to be using a specific room to learn about enumerating web services. It's going to be the DVWA room from tryhackme.com. So if you don't have an account over at tryhackme.com, you can make one for free, and you can access the room we're going to be using from this link over here. So I'll show you guys what it looks like when you access this room for the first time. Just a second. So after you've logged into TryHackMe, you want to access this room over here. So it's called DVWA, and to get access to the room and all of its stuff, you need to click on the green Join Room button. Nose Neaton Go idea. Let's see. For me, the evil twin is the best method for network hacking. So that's a specific type of network attack. Anyways, okay. So after we've joined the room, what we need to do is we need to set up our virtual environment in task number 1. So click on task number 1, and then click on the green lab machine start lab machine button over here, and also the start attack box button. So after you've done that, click on this button labeled start attack box. This is going to start up a machine that we're going to be using to interact with the DVWA machine. So it's going to take about 2 minutes to initialize, but in the meantime, we can talk about the tools we're going to be covering today. Okay, so we're going to be doing something called directory busting. So directory busting, often just called dir busting, is the act of determining which endpoints, which files and directories, exist on a web app by trying to access those endpoints. It is a type of brute force attack. So a lot of people don't. A lot of people categorize brute force attacks as something that is only done to determine what password might be for a user account. But directory busting, trying to find out what directories and web pages exist on a website, this is also a type of brute force attack. So all these types of brute force attacks they can be detected by people monitoring their logs. And if you do a dir busting attack against a web server, it is going to be detected if people are monitoring. So the first tool we're going to be talking about is the derb tool. So the derb tool is an older directory busting tool. It's a very good first program to run on a web server because it's very easy to remember the command syntax. It's just derb and then space and then HTTP and then whatever domain or IP address you want to access. Okay, can I have your GitHub for learning? Yeah. We've got a bunch of education resources over here. So the derb tool. So the command syntax is very simple, and we can use it to try to figure out a few common endpoints for a particular web route, for a particular web server. Okay, the command syntax is very simple. The word list it uses is very good for enumerating older web servers and web apps. And let's go back to the TryHackMe page to see if it's started up. Okay, it started up now. So in the attack box over here, the first thing we want to do is we want to click into the terminal, and we want to hit enter to dismiss this welcome message. So the attack box it's a Linux virtual machine with a bunch of different cybersecurity tools we can use to interact with different virtual machines on the TryHackMe network. So the first thing we want to do inside of the attack box is we want to open up a terminal. So there are terminal shortcuts up here, over here, and over here. So you want to click on one of those, and this will give you access to the terminal where we can run our commands. The other thing we want to keep track of is the IP address. So there's an IP address for the DVWA machine, which is this one over here. So the one with the black box icon. Okay, Shota says, I'm working on the SLA1 program on TryHackMe. The SLA1 program. Oh, the SAL program, right? You're talking about SAL1 from TryHackMe? So this is the Security Analyst Level 1. Yeah, no worries. So this is a defensive cybersecurity certification. If you want to learn more about it, it's over here. Okay, so what we want to do is we want to take note of this IP address. The IP address is going to be different for each of you. Just remember to take note of the one beside the black box icon. Since 10.145.140.231, and we want to run dirb. So dirb, because dirb is a web enumeration tool, we need to include HTTP : / before the IP address. When we run the tool, it's going to let us know which endpoints are available on the machine. Shota says, additionally, I slowly progressed AI security modules as well. Yeah, so AI security modules are very, very popular these days because everybody's trying to deploy more AI applications. Okay, so what did we find? So we found on this particular website, there's a config endpoint, there's a docs endpoint, there's an external endpoint. So what we can do is we can start up the web browser inside of the attack box, and we can try to look at some of these endpoints. Okay, it's going to take a couple of seconds for the Firefox browser to run. So remember that this is the Firefox browser inside of the attack box, not on our local host. So we'll go to http : 10.145.140.231. So it's basically the same IP address that is the one over here. Okay, if we navigate over to this page, this is the DVWA application. Okay, and so we can minimize this. So remember, the derb tool was able to identify a bunch of folders and web pages. So it identified that there's a config directory, a docs directory, and an external directory. Let's try each one of these. So let's see. Config docs external. So we'll go over here. We'll replace login.php with config. Okay. So this is the configuration directory for the application. So because we can look at this and see all of the files inside, this is an example of something called directory indexing, which is a security vulnerability. So there was the config endpoint, there was also the docs endpoint. So docs. So these are more This is more directory indexing, which is not great. So we also found an external endpoint, and this leads to more directories we can look inside of. So the reason we were able to identify these endpoints is because we used our tool, our derb tool, to identify them. It also pointed out that there's a php.ini file, and there's a phpinfo.php page as well. So, I mean, generally, you don't want your PHP info to be available for everybody to see. So we can go back to Firefox, phpinfo.php. So over here, we'll just go to navigate directly to phpinfo.php. And this redirects us back to the login page. So this is pretty good. It doesn't actually give us our PHP info. We can also go to php.ini, which is another endpoint we found. This file attempts to overwrite the original php.ini file. So this is a configuration file for the PHP engine. So it also lets us know that there's a robots.txt file. So we'll move on to the next tool. So the next tool that we've got is the Nicto tool. So we just type in Nicto. Well, let's talk about this tool first. So the derb tool, we use that one to try to figure out common endpoints on the web server. There's also the Nicto tool. So the Nicto tool is not a directory busting tool necessarily, but it's a web app vulnerability scanner. So it's a very, very old one though, which attempts to ID insecure configurations and general web app settings. So when you run the Nicto tool on a particular website, it's going to try a bunch of different tests. So like derb, Nicto is also an older tool that is better suited to finding vulnerabilities on older web servers and web apps. And it also has a very easy to remember command syntax. So to run Nicto, just type in Nicto and then -h for host, and then the domain for the particular web page. So let's go ahead and go back. So Nicto-h, and then the address. Okay. So when we run the tool, it's going to give us a bunch of information about the web server. So it lets us know that this is an Apache web server that is probably running on Ubuntu. Okay, so there is a lack of a security flag on the PHP session ID cookie. It lets us know the version of PHP via the x-powered by header. And it says that the root page, or the landing page, redirects to login.php. There's also a robots.txt file that is available for us to look at. And it also contains one entry that should be manually viewed. So it's a pretty good little tool, especially for older web apps. If we go over to, we go over to the Firefox browser, and then we navigate over to robots.txt, which is one of the endpoints that was identified by Nicto. So it says user agent star, which means that any user agent can access the page. Disallow. Okay, so it doesn't want web crawling robots to index the landing page for some reason. But yeah, robots.txt is a file that it's used to indicate which files can and cannot be indexed by search engines. It's pretty commonly found in easy level web app security CTF challenges. But let's talk about the last tool that we're going to be exploring today. So that was the Nicto tool. So the last tool we're going to be talking about today is the GoBuster tool. So GoBuster is a very powerful directory busting tool, much more powerful than derb. However, its command syntax is much more complex. So when we run GoBuster, it's there's a number of different arguments you have to give in the command to have it work. So the first thing you have to do when you run GoBuster is you need to give GoBuster the dir parameter, dir, which instructs GoBuster to work in directory busting mode. The next thing you need to do is you need to specify the file extensions you want the program to look for with the -x parameter. Then provide a number of extensions to search for. Here we're searching for HTML files, but you can search for a bunch of different extensions at the same time. Then we provide a mandatory parameter, the -u parameter, which lets us provide the URL of the web app that we want to scan, which in this case is HTTP, this one over here. So the last thing we need to do when we run GoBuster is we need to give it a word list. We have to supply another mandatory parameter -w, which is the word list to use for the dir busting attack. A common list to use for CTF exercises is the directory list 2.3 medium.txt list. So let's take a look. So over here, the first thing we're going to take a look at is we're going to take a look at the word list we're going to be using. So cat user share word lists dirbuster, I think. Directory list medium. Directory list 2.3 medium.txt. Okay, so what this is, it's a list of different endpoints that might exist on a target. So let's pipe this out. Let's just use less. So it's just a list of possible directory names or page names. So index, images, download, etc., etc. They've got, I think this list has like 40,000 or like 100,000. Let's find out. So let's run the word count. So this is 218,000 words. So what we would do in this directory busting attack is we would check each one of these words as a directory or a web page with whatever web application that we'd want to test. Okay, so what we're going to do is we're going to run GoBuster, which is the tool we're talking about, and we're going to run it in directory busting mode, and we're going to give it a URL, which is HTTP and then our IP address over here. So 10.145 10.145.140.231. We're going to give it a word list, and we're going to give it some extensions. So -x, and then we can look for HTML file extensions. We can look for PHP, we can look for TXT, back, zip. So if we're giving more than one, we need to separate these by some commas. Okay, when we run the tool, it's going to go through all of the words in the directory list 2.3 medium.txt file, and it's going to try to see if these endpoints exist on the web server. So we managed to find .php, .html, index.php, about.php, login.php, just a bunch of different pages. And it also lets you know what response it received from the web server. So 302 means it redirected us, 200 means it was okay, 403 means it was forbidden, and 302, everything in the 300 range is some sort of redirect, everything in the 200 range is an okay response, and everything in the 400 is an error response. So through this kind of method, you can find out what pages exist on the web server, and then start visiting or enumerating each one of these for particular vulnerabilities. So we also have, if you ever encounter something that looks a little bit unusual, you can manually check it out. So copying.txt or instructions.php. Let's try taking a look. So over here, so what was it? Copying.txt. Okay, so this is a GNU General Public License for some sort of software. And there's also instructions.php. Let's try checking it out. Okay, so this basically tells us about what we're supposed to be doing with the DVWA application. So this is an application with a bunch of software vulnerabilities. Sorry, not software vulnerabilities. A bunch of web application vulnerabilities that you can use to learn about different types of web app hacking. But we're not really here to learn about web app hacking, just about web app enumeration. Okay, and I don't know how to pronounce your name. Thami Palkamana? How many years do you have in this domain? If you're asking me how long I've been studying cybersecurity stuff, well, I started learning cybersecurity in 2020. I wouldn't call myself an expert after like 5 years of learning about cybersecurity, but I do have a number of years studying the subject. Anyways, okay. So this is how you would do dir busting. Directory busting using a few different tools. So there's GoBuster, we use Derb, we use Nikto, and we use GoBuster. So some people think that GoBuster is kind of an old tool to use as well, but it's pretty standard. And all three of these tools you will find very commonly on security distributions of Linux, such as the TryHackMe attack box, as well as on Kali Linux. So typically, if you wanted to find out if a particular program is installed on your Linux system, you'd use the which command. So which derb, which Nikto, and which GoBuster. This lets you know where these are installed, and they also this command also lets you know if these tools are installed in your system. Okay, if you have any other questions about web app enumeration, or if you have any other questions about web app enumeration, let me know in the chat. I'll try to answer your questions as best I can. So if you're looking for another commonly used tool for directory busting, Ferrix Buster is also another very commonly used tool. I don't think it comes installed on Kali Linux by default, but you can find the GitHub repository over here. Okay, I don't understand everything you're doing because I'm French. It's cool to see the ease with which you're doing this stuff. Yeah, I mean, if you want to, there's actually a French website that has a bunch of security challenges on it if you want to take a look. So this is managed by the French cybersecurity, some sort of French cybersecurity organization. But take a look. Take a look at it if you're interested in solving cybersecurity challenges. Okay, where was I? But yeah, there's a lot of information that you can get from the web server just by using some tools. So the other thing you can do is, another very common tool we use in security testing is curl. So curl is a way of contacting a web page without having access to a web browser. So typically you would run curl and then you would give the IP address. So curl 10.145.140.231, and this also gives you a number of different request and response headers, which can be very useful for web app enumeration as well. So when you send this request, these are the request headers that you send, and the response headers that the server sends back are over here. Huh. Oh, okay. This sends you to the login page. All right, so I think we're just about done with this lesson, and let's do our summary. So let's review the network hacking concepts we learned about in this workshop. Directory busting. So directory busting is the act of determining which endpoints, which files and directories exist on a web app by trying to access those endpoints. This is a type of brute force attack. So we can use a number of different tools to do to do directory busting, such as DIRB. So it's an older directory busting tool, but it's also a good first program to run on web servers. So there's also the NICTO tool, which is a web app vulnerability scanner, which attempts to ID insecure configurations and general web app settings. And there's the GoBuster tool. So GoBuster is a much more powerful directory busting tool. However, its command syntax is much more complex. So what I'd suggest is, if you've ever used a tool and it's got kind of complex command syntax like dirbuster, what I'd do is I would copy the command syntax and then include it in my notes. So for example, if you've got GitHub, you might want to write some notes on each tool and then include some sample commands. So by including the sample commands, it means that you don't have to look up how to run the tool every time you use it, which can be a big what is the word? A big time commitment. Yeah. Okay, so I think that's all we have for this. So in the next HackerFrogs After-School Network Hacking Workshop, we're going to be learning how to create reverse shells and bind shells to create connections between network computers. So this is it's a pretty fun lesson because part of the fun of network service hacking is getting direct access to vulnerable servers. So getting that reverse shell, it's a big part of what makes network service hacking great. Anyways, that's going to be on the next lesson. So the next lesson is going to be on Wednesday of next week. So come back next week on Wednesday, and we're going to be covering more network hacking techniques. Okay, so I think we've got a bit of spare time, so I wonder if there's a challenge we can do from Scilab that covers the same sort of stuff we're learning today. So Scilab Academy is a very good resource for learning about cybersecurity in general across a bunch of different categories. And what I'm going to do, I'm going to start looking for some web app security challenges over here. Maybe we can try to solve one or two. Okay, weekly pickups. Caught the ending with GoBuster. Do you drop your videos on YouTube or on Reddit? Yeah, we generally cover a bunch of stuff from different CTF challenges. Not necessarily these lessons themselves. These lessons you can probably go back to on our YouTube channel. Oh, I don't have a YouTube link. Okay, let me drop the YouTube link. Just a second. So this is the YouTube channel over here. You can also go back in the VOD in Twitch if you want to catch the stuff we did previously in the live stream. Okay, let's look for a web app challenge. maybe an easy one. And then let's take a look at what shows up. So we got old sessions, crack the gate, no sanity, head dump, SSTI. Okay, let's try this one over here. Okay, so normally these type of challenges, you'd access them from a web browser, but let's try accessing it. Well, let's try interacting with this challenge from the terminal. So click on Launch Instance. And then click on Open in Workspace. So when you click on Open in Workspace, it's going to open up a terminal that has access to it. This terminal should have access to the web to the servers that you start up in the challenges. So you can right click on it. Actually, maybe yeah, we can right click on the terminal here. You can click on this. You can select this frame, and then choose Open Frame in New Tab. Okay, so this will give you web shell access, which is terminal access. And what we're going to do is we're going to click on Exit Workspace up here. And then we're going to get the link for the challenge. So it says, there's a link that says Browse here. Right click on this and then select Copy Link. Then go over to the web shell. And then paste in the link. Okay, so this is the website that we're going to be interacting with. So we're going to see if we can let's see if these tools are installed in the first place. Yeah, so okay. So which derb? There's no derb installed. What about Nicto? There's no Nicto installed. What about GoBuster? There's no GoBuster installed either. Huh, so they haven't installed any of these tools on the Scilab terminal. That's good to know. Okay, there's probably curl. There is curl, so we could access this web page from curl. Just type in curl-v and then copy and paste. Oh. Okay, copy this, go back to the web shell, paste this in. And so we're going to be accessing the web page from curl. So this lets you know which HTTP request headers you sent. So the host header, the user agent header, the accept header, and then we see which ones were sent in response. In this case, it's the server header, the date header, content type, content length. So, I mean, I guess we can't really access this from, we can't really use our tools because the tools aren't installed. So if you've got access to a security distribution of Linux, like Kali Linux or Parrot OS, then you could access this this page over here. So I'll just give this to everybody. You can give it a try. So you can run derb. This is not going to be very fast because these two machines are not on the same network. We have to access it over the internet. So when we run derb, we try to run a directory busting attack. And actually, wait. When we run derb, we shouldn't be running this on the login endpoint. When you run derb, it should be at the web root of the application. Okay, Shota says, hi, thanks for the stream. We got to run. See you next time. See you next time, Shota. Okay, and we're only checking 4,000 words in this case. The word list for derb is pretty short. And make it faster. Can I make, well... Okay, so this is a machine on the open internet. It's not on a private network. But the good thing about these machines on Scilab is that you're able to run your tools against them, and they don't mind. So some other websites, if you start running security tools against like random internet websites, people might not be might not be super happy with you running those tools against their web pages. Are BYD cars safe for privacy? Do you know? I wouldn't know. I don't know very much about smart cars. Sorry about that. Okay, we weren't able to. It looks like we're not really able to find anything with Derb. It's also pretty slow because we're still in the C's in our word list. So the other thing we could do is we could also run Nikto against this particular website. So Nikto-H. Nothing smart is good for privacy. If it's smart, then it's not smart. So Nikto also gives us some information about the web page. So it says that the server that is being used is a work Zug server, which is a common type of server software. Well, it's a common designation for a Python-powered web server. Okay, and it also tells us that root page redirects to login, which means if we go to the web root, it directs us to the login endpoint. Okay, how much should I know before I call myself a hacker? You can call yourself a hacker immediately. Thank you very much for... Oh, I missed it a couple minutes ago. Thank you very much for following on Twitch. Troika, thank you. How much should I know before I call myself a hacker? Calling yourself a hacker is more like... It's more about philosophy than actual skill. Because let's think about this, right? So what is... I guess we should talk about what hacking is first. What is hacking? Hacking is interacting with systems in an unintentional way. Unintentional manner. Unintentional manner which benefits the user in some way. It's actually a very broad definition. So hacking, some people say that hacking is taking advantage of computer systems. You don't need a computer system to hack. It's interacting with the system in an unintentional manner, which benefits you, which means that hacking can be... So there's social interaction hacking. There's also hacking the law system, hacking the tax system. It's taking advantage of rules inside of systems. You can call yourself whatever you want, making a system do something that wasn't intended. So let's suppose, you have a friend. You have a friend who is mad at you. Okay? You have a friend who's mad at you. They're yelling and screaming at something you did. Okay? But they can be distracted if you mention their favorite sports team. Let's say that they're, a really big, I don't know, what's the Team Canada soccer fan. Okay, so to distract them from being angry at you, You mentioned Team Canada and their recent game. They forget they're mad at you and talk about soccer. Okay, this is a hack. You interacted with them in a way that benefited you. Okay, brother, are you a pen tester? I didn't make the rules. So you're Canadian, you have to use hockey. Oh, okay, okay. I mean, everybody's talking about soccer these days. Ski, hello, nice to see you here. Are you a pen tester? I've worked as a pen tester in the past. I'm not working as a pen tester right now. That benefits you? So, how much do you need to know to call yourself a hacker? It's up to you. It's up to you. You can call yourself a hacker, you can not call yourself a hacker. If you call yourself a hacker, it comes with all sorts of baggage. People will expect you to know everything. Some people's definition of hacker means that you have to know. Hacker is a very loaded term. Just know that if you call yourself a hacker, then people are going to expect you to know a bunch of stuff. One of the best hackers was the social engineer Kevin Mitnick. I mean, Kevin Mitnick did a lot of social engineering. He also did like technical computer stuff as well. Anyways, okay, we've got a bit of time left before we start the last thing today. What is the last thing today? Oh, public key cryptography over at CryptoHack. If you want to learn, well, if you want to get ahead of what we're going to be doing in just a little bit, this is the course we're going to be doing over at CryptoHack. So I think cryptography is really cool. Unfortunately, I'm not very good at math, but we're going to be doing that. Well, we'll do this stuff in about 15 minutes. Meanwhile, I'm trying to figure out this Sudoku puzzle. I am really bad at Sudoku. Okay, let me go ahead and reset this puzzle, and I'm gonna try to figure out what the heck is going on over here. So you got 15 minutes. Hacking is all about interacting with different systems. So each puzzle we can think of as a different type of system to interact with, and figuring out how to interact with systems is a very important thing for every hacker to do. It's just that I'm garbage at Sudoku. Okay, so what's going on here? We begin with only one number. We begin with only one of each number, so one of them must block off enough cells in another region for you to place another number. So let's see. One of them must block off enough cells in another region. Oh, okay. So there's a 3, 4 here, and there's a 6 over here. 3, 4. We know there's a 5 here. We know there's a 6 here. So this puzzle relies on a useful trick. If we know a few cells must have some set of numbers, even if we can't place them, what does that tell us about other cells in the same row or column? So 1, 2, 3, 4. So this is a 6. There's a 1, a 2, 1 and a 2 here. There's a 3. So this has to be 6. Because the 1 and the 2 mean that in these rows there can't be a 1 or a 2. look at the top three cells in the rightmost column. The top three rows, top three cells in the rightmost column. So this set of cells over here, what numbers must they be? What does that tell us about the rest of that column? So this this region over here has to have the numbers 1 to 6. Each one of these rows has to have 1 to 6, and each one of these columns has to have 1 to 6. So that tells us that there's got to be the numbers 1, 2, and 5 in these three over here. So 5 can't be... This can't be 1. This can't be 2. Yeah, if anybody here is really good at Sudoku, let us know, because we need to figure this out. I mean, I guess we could also skip this one, because I've spent a lot of time covering this one. Let's skip over to the next puzzle. Okay, here's the link. Okay, so the lockmaker, remaining ever evasive about the solvers, reluctantly agrees to offer a tiny clue if the questions will stop. So this is... Oh, it is a picture-based puzzle. Okay, so what are we supposed to do here? So look for the hidden clues in the puzzle image and try to find the secret word. Once you think you've found the answer, type it in and press submit. Okay, so the image is this one over here. So let's see. Huh. So this symbol equals 1, and this symbol equals 2, and this symbol equals 3. So I guess we're taking a look at these keys, and we're trying to figure out L equals L. So I think we're trying to figure out if these keys are associated with the letter. So L is triangle 2, 2 and 3, and 2 and 3 and 2. So 2 triangles, which are 2 each, and a rectangle, which is 3. 2, 2, 3. 2, 2, 3, and then let's think about this. Okay, we got L equals 2, 2, 3, something, and then 2. So there's this shape this shape here, so this diamond shape one. And I guess we need to assign some sort of number for this as well. So this diamond shape thing is probably the number 4 or the number 0. So there are 4 shapes. There is the circle shape, or guess what do we call that? So the curve equals 1. triangle. The triangle is 2. Oh, I didn't spell triangle correctly. The curve is 1, the triangle is 2, the rectangle is 3. And then there's the diamond, which I assume is going to be the number 4. It's either the number 4 or the number 0. 4 or 0. So the letter L is 2, 3, something 2. Because we've got the diamond shape where the question mark is. So that means that this is either 2, 3, 4, 2, or 2, 3, 0, 2. So how does it make sense that the letter L is these numbers? So if we think about the position where the letter L is in the alphabet, where is L in the alphabet? Okay. A, B, C, D, E, F, G, H, I, J, K, L, M, N. So this is the halfway point in the alphabet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So L is the 12th letter in the alphabet. L, 12th letter. So are they adding these numbers together to get the number 12? 2 plus 3 plus 4 plus 2. So it's 5 plus 6. 5 plus 6 is 11. So if we're adding up these numbers, then the diamond has to be the letter 5. If we're actually doing this off of positions in the alphabet by adding up these numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So L equals 12. So we do get there if we do 2 plus 3 plus 5 plus 2. So this is 7, 7 plus 5, 7 plus 5 equals 12. Okay, let's take a look at these other keys. So first position is triangle, triangle, circle, circle, triangle, circle, triangle, triangle, curve, curve. So first position is triangle, curve, triangle, curve, which is 2, 1, 2, 1. If we add up these numbers, then we get 6. So if we're going by position in the alphabet, the sixth one is 1, 2, 3, 4, 5, 6, the letter F. Okay, so that's the first key. The second key is diamond, triangle, diamond, rectangle, diamond. Okay, let's record this. Diamond, triangle, diamond. Diamond, triangle, diamond. Rectangle, diamond. Rectangle, diamond. So if we're assuming that diamond equals 5, then that's 5, 2, 5, 3, 5. So that, what does that equal? It's 10, 15, 20. So this is the 20th letter in the alphabet. If this is the 20th letter in the alphabet, then that's N, O, P, Q, R, S, T, U, V, W, X, Y, Z. So this is 13, 14, 15, 16, 17, 18, 19, 20. So this is U. So F U. I don't know. I don't know if this is actually the way we want to do it, because I'm pretty sure they wouldn't use bad words in their puzzles. So this is what? The third letter is curve, curve, triangle. Curve, curve, triangle. Curve, curve, triangle, which would be 1, 1, 2. So 1, 1, 2 is 4. The fourth letter in the alphabet is 1, 2, 3, 4, D. So F-U-D. And what's this last one? So the last one is just curve and triangle. Curve, triangle, that is 1 and 2, which equals 3, the third. Okay, so I think this is not the way we want to do it. So L, I guess we can get some help on this. So look for any clues that might indicate the format of the answer and work backwards from there. Find connections between different elements of the puzzle. Not all details will be important. Finding the answer may require multiple steps. If the answer seems like gibberish, it's probably not correct. Okay, let's get some hints for this. Hint 1. If the top key represents L, then maybe the other keys also represent letters. So, I mean, yeah, I think we caught on to the fact that this is supposed to represent like 4 letters. Okay, so the next clue, if the cutout notches represent numbers, how do the notches on the top key correspond to L? So yeah, we're trying to figure out 1, 2, and 3. So the triangle represents 2, and then 3, and then something, and then 2. I mean, I assume that it was supposed to have something to do with the position of the letter in the alphabet. So L is the 12th letter in the alphabet, and these numbers have to add up to 12. But maybe that's not the case. Okay, what else do we have? You've not been given the number for one of the notches, but can you work it out? Is there a pattern? Is there a pattern? So here we know that the shapes represent different numbers. Oh, the number, okay. So the number of lines. So this is one line. This is two lines because you need two lines to make the triangle. This is three lines because you need three lines to make this rectangle type shape. And this is 1, 2, 3, 4. So this represents 4. The diamond represents 4. Okay, let's go back. So the diamond probably represents the number 4. So if we take a look at the first key, it's triangle, curve, triangle, curve. And we're guessing that this corresponds with the letter F. But then again, if L is 2, 3, 4, 2, then these numbers taken together are 5 plus 6 is 11. So L equals 11. Now, how does L relate to the number 11, though? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 is the 11th letter is K. So how do these four numbers 2, 3, 5, 2, no, 2, 3, 4, 2, how does this represent the letter L? Okay, let's get another hint. Okay, do things not seem to add up quite right? Curious. Oh, you know what? Maybe it has to do with the circle. So the circle represents 1. The circle represents 1, and this triangle represents 4. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this does match up with the position of L in the alphabet, which is the 12th letter. So that means that this one is 1, 2, 3, 4, 5, 6, 7. And the 7th letter in the alphabet is 1, 2, 3, 4, 5, 6, 7, G. So first one is G. Okay? And that means the second key is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the 18th letter in the alphabet is we're looking for 18. 13, 14, 15, 16, 17, 18, S. So GS, it's already seeming, Let me double check. Let me double check the number of strokes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, and then we need to double check that 18 is S. 13, 14, 15, 16, 17, 18. So 18 is S. So it's GS. And then we've got 1, 2, 3, 4, 5. Okay. Lol, that's me. Hello, nice to see you here. Hope you're having a good time. So how many is that? 1, 2, 3, 4, 5. The fifth letter in the alphabet is one, two, three, four, 5 is E. GSE something. 1, 2, 3, 4, 5, 6, 7. And the seventh letter in the alphabet 1, 2, 3, 4, 5, 6, 7 is G again. GSEG. This doesn't make any sense. Okay, let's go ahead and get another hint from this thing. Other than notches, are there any other differences between the keys? So some of the keys have circles, and the last key has a square. Okay, one of the keys has something slightly different to the others. Perhaps that might help your numbers add up correctly. What do the numbers actually represent? It's not just the shape, but it's the number. It's not just the shape, but the number, right? Okay, so it's the number of lines you need to do to make the shape. Have you been counting every bit that has been cut out of the keys? That's been cut out of the keys. 1, 2, 3, 4, 5, 6, 7. So for the letter L, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to make the letter L, which is the 12th letter in the alphabet. Ender Kira, hello, nice to see you here. What is up? Hope you're having a good time. Hope you're having a good Friday afternoon, Friday evening, wherever it is where you are. Huh. So it's a 4-letter word that's spelled out with these keys. 1, 2, L equals this thing. I thought it was the number of lines in the notches, but it's I don't know if it is. Does anybody else have some sort of clue or a theory? If you have an idea of what this might be, so L has to be this key. Yeah, no problem, Ender Kira. Okay, so 1, 2, 3, 4, 5, 6, 7. So 7 is G, the letter G. Because if we're going by the 1, 2, 3, 4, 5, 6, 7. You had GSEG. You were one off. If you were one off on the second one, it would have been Greg. Greg? Was I one off on the second one? So the second one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So is it... one of the keys is something slightly different to the others. So, I mean, Greg is somebody's... I don't know. Do we submit Greg? What? Isn't that the bookboard? Okay. Greg, but I don't understand. Is it supposed to, is that supposed to be one off? So R. What position is R in? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13. Oh, no. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, I am one off. I'm one off because this is not the 13th position. This is the 14th position. My number counting was wrong. Wow, I feel dumb. So that was it. That was it. It was the number of notches, and then the number of... Yeah. So if you count incorrectly, you don't get to hack. That was a big typo for me. The shy 31 typo. There you go. 20 demerits. Yeah, for sure. There's my typo emote. Anyways, let's go ahead and move on to cryptography. So I'm gonna give myself 2 hours to do this this course on cryptography. And we're talking about public key stuff. So public key cryptography. This is a course from CryptoHack that you can find over here. So I'm gonna redo the lessons that I did previously, because it's not gonna make a lot of sense if I don't go back to the beginning. Your take on Apple prices? I don't... Well, I mean, are you talking about Apple electronics? Are you talking about Apple phones? I don't use Apple, I use Android. But, I mean, Apple stuff is always way more expensive than Android stuff is. Macs and iPods, yeah. If you've got any Apple users in chat, let us know. Okay, I've been doing this course because I want to learn more about cryptography. And I've been trying to keep track of... This is how I'm trying to cover teaching myself new skills. So this is public key cryptography. We've got a bunch of different challenges that we're doing in here, and this is how I'm trying to take my notes. If you want to keep up with my notes for public key cryptography over here. Those data centers cooked us. Mac RAM and SSDs. Mac RAM and SSDs. They've gone up 50%. Whoa. The prices went up due to RAM circuit shortage. I'm sorry to hear that. That's why I mean, I've only ever owned one Apple device. I think it was like an iPhone 3. And I really didn't like using the iTunes store to put stuff on my iPhone, and that's why I stopped using it. Okay, let's talk about what this course is. So this course is on public key cryptography. Whitman Diffie and Martin Hellman's 1976 paper on new directions in cryptography heralded a huge leap forward for the field of cryptography. The paper defined the concepts of public key cryptosystems, one-way trapdoor functions, and digital signatures, and described a key exchange method for securely sharing secrets over an insecure channel. Persona Management says, don't forget 30% of AWS data center storage is CCTV feed. 30% of AWS data center storage is CCT feed? Well, I mean, that doesn't seem implausible because CCT footage takes up a lot of hard drive space or storage space, I guess. Okay, I was thinking about between getting a ThinkPad and a Mac Pro. I guess it's decided now. Well, I mean, it really depends on how much you enjoy using Apple devices and what is the term? How embedded you are into using Apple services. Okay. So although these were independently discovered at GCHQ some years earlier, Diffie and Hellman were the first to share this landmark knowledge with the world. So public key encryption. So this enables a user, Alice, to distribute a public key, and others can use that public key to encrypt messages to her. Alice can then use her private key to decrypt the messages. Digital signatures enable Alice to use her private key to sign a message. Anyone can use Alice's public key to verify that the signature was created with her corresponding private key and that the message hasn't been tampered with. Persona Management says those Ring cameras got us paying more for SSDs. I mean, a lot of people have a lot of issues with those Ring cameras. I don't use the Ring cameras myself because I don't like the idea of other people being able to use my camera for their benefit. So although Diffie and Hellman's paper is legendary in cryptography, it was the RSA algorithm described a year later, which was the first full public key crypto system. This course gets you familiar with this extremely famous crypto system and all the concepts described above. RSA security is based on the difficulty of factoring large composite numbers, still considered a hard problem, but in recent years the crypto system has received criticism for how easy it is to implement incorrectly. The return of Alice and Bob. Alice and Bob like to exchange messages. Major flaws have been found in common deployments, the most notorious of these being the Roke vulnerability, which led to Estonia suspending 760,000 national ID cards. So our challenges first introduce you to the many foot guns. What is a foot gun? A foot that you can shoot yourself. The foot guns of RSA, and soon you will perform attacks which real software has been vulnerable to. Next, you look at Diffie-Hellman key exchange and explore how the core problem behind it, the discrete logarithm, differs from RSA factorization. The course concludes with you performing man-in-the-middle attacks on two people trying to exchange encryption keys. A gun that shoots you in the foot. I guess that makes sense. Software engineers use that a lot. Okay. This is new information to me. Okay, so the first thing what we're going to be learning is modular exponentiation. Let's go ahead and start. So this is me introducing this information to you all, and then trying to understand. I've solved these. I've solved some of these problems, but I'm trying to better understand how they work. So all operations in RSA involve modular exponentiation. Modular exponentiation is an operation that is used extensively in cryptography and is normally written something like 2 to the power of 10 mod 17. Okay, Dr. Drico Morad, hello, nice to see you here. I'm not an expert, but I saw a lot of blogs stating that cryptography will be a big issue once quantum computing starts being a thing. Do you know more about it? SysOS Master says, a foot gun is a mechanism that you would automatically shoot yourself in the foot. It's a metaphor for traps, easy mistakes, or tricky implementation in software. Thank you for that, SysOS Master, and welcome to the stream. Drick Morad So quantum computing is a thing that might result in a lot of cryptography being broken, because cryptography was made with modern computing in mind. But there's a lot of cryptography that is made to be quantum resistant. So quantum resistant cryptography, which is going to resist the advent of quantum computing being a thing. I hear that it's slowly being rolled out. SysOS says the heat crashed my local network with over 38 degrees Celsius. In Canada, we got a lot of rain today, and that cooled us down a lot. So Vancouver weather. Actually, let me do this offline to see if it doesn't reveal my location. Yeah, that might reveal my location. But anyways, it's currently 16 degrees Celsius. Well, no, it's 16 degrees Celsius right now for it, so it's pretty cool where I am. Okay, so modular exponentiation. Unfortunately, I can't really write this out very well. So the best I can do is something like this. So 2 to the 10th power is 2 to the power of 10, and then mod 17, I would write it like this. So this is Python syntax. So this is, whoops, 2 to the power of 10 modulo 17. Celsius. Yeah, I mean... Wait, do you not use Celsius, April? I thought you were in, Are you an American, or are you in another country? You don't need to answer if you don't want to. So this is how I'm going to have to write out exponentiation, because I can't very easily write it out using ASCII characters. Every hacker should probably watch this scene from Good Will Hunting. Oh, you're American. Okay, no worries. Except for the world except for 2 countries use Celsius. What's the second country? I know America uses Celsius, but what's the second country that uses I know America uses Fahrenheit, but what is the second country that uses Fahrenheit? Okay. So you can think of this as raising some number to a certain power. So to the power of 10, which is 1024, and then taking the remainder of the division by some other number. So mod 17. So divide by 17 and take the remainder, which is 4. In Python, there's a built-in operator for performing this operation, the pow function. So pow, give it a base, an exponent, and a modulus. Liberia. Oh, interesting. April says it's definitely the rest of the world that is wrong. Of course, it has to be, right? Okay, in RSA, modular exponentiation, together with the problem of prime factorization, helps us build a trapdoor function. That is a function that is easy to compute in one direction, but is hard to do in reverse unless you have the right information. It allows us to encrypt a message, and only the person with the key can perform the inverse operation to decrypt it. Okay, so the pow function is something that we're going to be using a lot when we're dealing with RSA. So the power of the base, the exponent, and the modulus. It can run all of this. It can run all of this all at once. So we can run. I mean, we can do this inside of our Python. Let's call this our Python window. Okay, we'll just run our Python terminal here. And we can run pow. So pow base exponent modulus. So if we wanted to do 2 to the power of 10 modulo 17, then we can just run this function here. So we get the number 4. So 2 to the power of 10 divided by 17, take the remainder, that's 4. Cypher says 0 freezes, 100 boils. Why use arbitrary nonsense? I mean, the thing about number systems is that number systems, they're not always clean. The thing you can say about Fahrenheit is that it is more accurate than Celsius, because the numbers get bigger than Celsius. Anyways, so we've got modular exponentiation, which is represented by the POW function here. Okay, to grab the flag, find the solution of 101 to the power of 17 mod this number here. So here, it should be pretty easy to do this in Python. Although you could probably, so 101 to the power of 17 mod 22663, like this. Moracat, that's not true. Fahrenheit is defined as a unit that uses the same scale as Celsius, called Kelvin. I mean, I'm not an expert on this by any means. The other thing about I guess the other thing about Celsius versus Fahrenheit is that you can also subdivide Celsius, with like decimal points, and that makes it about as accurate as Fahrenheit is. Okay, so this is the number here. So 101 to the power of 17 mod 22663 is this number, and this is the number they're looking for this exercise. I've solved this challenge already, which means we don't need to test it. Although, I guess there's a bunch of other solutions that we could take a look over here. Oh no, I'm actually looking for the other solution scripts, although it doesn't really tell us. Oh, that's fine. Okay, then there are no solutions for that first one. All right, that's right. That's fine. Okay, so now we're talking about public keys. So RSA encryption is a modular exponentiation of a message with the exponent e and the modulus n, which is normally a product of 2 primes. So n equals p times q. So together, the exponent and the modulus form an RSA public key, which is composed of n and e, which is the exponent. The most common value for e is hexadecimal 10001, or 65,537. Okay, so what they want us to do, I guess we should probably talk about some of if you're learning about this, I guess a good thing to do is to take a bunch of notes about what these letters mean. So what is n? What is p? What is q? And what is e? And I recorded that over here. Hold on. CryptoHack. Is anybody here very familiar with cryptography, by the way? Because we could use a bit of help sometimes. Okay, the challenge asks us to encrypt the number 12 with an e value of 65537 and a modulus n, which is p equals 17 and q equals 23, which products out to 391. I got PTSD from these letters. I've done a bit in CTFs, not my strongest. I mean, this is what practice is for. It's for hopefully getting a little bit more confident with cryptographic operations. Randolph Stokes says, I had a little bit of cryptography in college. Awesome. That's great to hear. Okay. So it asks us to encrypt the number 12 with an E value of this one and in modulus n. And so that's essentially, so the calculation is 12, which is x. Wait, why did I put this x here? 12 to the 65537 power modulo 391. So XYZ is 12, 65537, and 391. And you can run it. We can run this particular operation with the POW function. P and Q are prime numbers. Yeah. So the modulus n is a multiplication of two prime numbers. So in this case, 17 and 23. So we can run the POW function again to get the number. So if we go over to our terminal, we run the POW function, the number 12 raised to this power, and then moduloed by 17 by the result of 17 times 23. And then we get the number 301 is the result. Is AI eating everybody's jobs? It's reducing the number of jobs in some roles, yeah. But I'm Kira, or I'm Kieran. Hello, nice to see you here. I think the important thing to do with all of this AI uncertainty going around is to focus on learning something to a high degree, so that when everything settles out, you'll be able to find your place in the new system. Okay, so this is how we calculate the answer in this case. And then we move on to the next. I mean, another good thing to do would be to take a look at other people's solutions. So if we take a look at other people's solutions for this challenge, is everybody using the Python? Everybody's using the Python function here. Okay, so this is the Python function. And then that's the highest rated solution. The highest rated solution is just to use the Python function. That's interesting. Let's move on to the next challenge. Okay, so Euler's Todian. I spent a while learning about this. So RSA relies on the difficulty of the factorization of the modulus n. If the prime factors can be deduced, then we can calculate the Euler's Todian of n and decrypt the ciphertext. Given n equals p times q, and p and q are co-prime, which means they're both prime numbers. So normally inside of RSA encryption, the p and the q value have to be large prime numbers. If the prime numbers are not sufficiently large, then bad things can happen. SysOS Master says crypto implementation with Python is typically easy due to the sheer amount of helper libraries and modules. Yeah, if you want to work a lot with cryptography, learning some Python is a very good thing to do, because you can do a lot of cryptographic operations using some Python scripts. Those are not considered large for RSA. Okay, Red Sly Fox says, if you're already a hacker and you can't find work, learn Chinese or Russian. Someone will find value in you. If you're already a hacker and you can't find work, I mean, I don't know about that advice, Red Sly Fox. I'd say definitely look for legal work and not illegal work. Okay, so given n equals p and q and two primes, so p equals, well, I mean these big numbers, what is the Euler's Todian of n. So n is the result of these two big prime numbers being multiplied together. What did I write for my notes here? So for my notes, this is the third lesson, Euler's todiant. Okay, so I basically rewrote the stuff that was presented in the lesson, but I did some research. We can calculate Euler's todiant for n with the following formula. So todiant of n is equal to todiant of p times q. So n equals p times q, basically, which is also equal to p minus 1 times q minus 1. So p minus 1 and q minus 1 is a very important part for the calculation of the Euler's todiant of n. So if we have some pure, simple prime numbers for p and q, so if we got 3 and 5, for example, some very small prime numbers, then the Euler's todiant of 15 is the todiant of 3 times 5, which is equal to 3 minus 1, so it's 2, times 4, which is 8. So the breakdown of this equation involves creating a list of numbers from 1 to n. So 1 to n, where n is 15. So a list of numbers from 1 to 15. Then we remove all the numbers that are multiples of the p and q values, which means all the numbers which are divisible by 3, and all the numbers that are divisible by 5, we need to remove those numbers from the list. Okay, and then after removal of all those numbers, we're left with these numbers over here, which is 8 numbers, which means the Euler's todiant of 15 is 8. Okay, the way we can calculate our Euler's todiant with Python is with this function over here. So phi is a function that takes an n. The result was going to be equal to n. Then take the prime factor, starting with the smallest prime factor 2. So I will admit that I had AI help with writing up the script, because math is not my strong point, and I needed to ask a lot of questions. Okay, we only need to test the factors up to square root of n, because if n has a factor larger than square root of n, the matching factor must be smaller than square root of n, and would have already been found. So while p times p is less than n, if n modulo p equals 0, and while n modulo p is equal to 0, then n is updated as the division of p. So apply the Euler's todiant update for the distinct prime factor. So update the result to be less the division of p. Then move on to the next possible factor, increase p by 1. So after the loop, if n is still greater than 1, then the remaining n itself is the prime factor larger than the square root of the original n. We must account for it. If n is greater than 1, result is decremented by the result of the division by n. The final result is the count of the numbers from 1 to the original n that are co-prime to the original n. Return result. Okay, but there's an even simpler Python script we can use if we know the values of p and q. So if we know the values of p and q, we can calculate the Euler's todiant from p and q with p minus 1 times q minus 1, which is much easier than this, because we know the p and the q value. So if we go here, okay, let's make a script. What is it called? Euler's Euler's taught. Okay, so this, I mean, we don't even really need to create a function here. So it's just p minus 1 times q minus 1. So todiant equals this. And we just need to plug in p and q. So p equals some big number and q also. So p equals this. Whoops, that was q. So p minus 1 and q minus 1, if we print out the result of that, we'll get our answer. So this big number over here. So this is the answer for the challenge. Randolph-Stokes says, it looks like the todiant returns the number of values that are not divisible by the factors. The number of values, yeah, the number of numbers. I have a hard time talking about the items in the set, right? So the items in the set that are not divisible by the factors is what we're looking for. So in the case that where the numbers are really big, then it's something like this. So we'll probably get a better result if we look at the scripts that were written by people who know way more about math than I do. So the let's see, I think this is the one with the best score. Okay, this is exactly what I wrote. I swear I didn't copy this one. I just started asking questions. Okay, so Euler's. Oh, am I not pronouncing it correctly? Hard name for English speakers to pronounce. You explained it well. So how do you pronounce this name? Euler? Yeah, that's hard for English speakers to pronounce. Euler. Huh. I don't know if I'm gonna keep on pronouncing it Euler because it just seems a lot easier. Sounds like Euler. Okay, I'll try saying Euler instead of Euler. Euler. Anyways, let's move on to the next lesson. So the next lesson is talking about private keys. So the private key D is used to decrypt ciphertext created with a corresponding public key. It's also used to sign a message, but we'll get to that later. The private key is the secret piece of information or trapdoor which allows us to quickly invert the encryption function. So I think you were saying todiant wrong too. I think it's like quotient. Totient? Totient, not todiant. I'm sorry. I'm very new. I'm very new to these terms. I don't do a lot of math. Sorry about that. Totient. So it's Euler's totient. Hold on. Let's talk about those. Okay, so we're talking about so this is not Euler's todiant. It's supposed to be Euler's This is supposed to be Euler's totient. Okay, it's very clear you're not taught you're not taught in this part of math. No shame. The names are European in origin, not English. Oh, okay. Totient quotient. Anyways, I'm trying to better myself. I appreciate all the feedback from the people in chat. I need to educate myself. Okay, so the private key D is used to decrypt ciphertext created with a corresponding public key. Okay? The private key is the secret piece of information or trapdoor which allows us to quickly invert the encryption function. If RSA is implemented well, if you do not have the private key, the fastest way to decrypt the ciphertext is to factorize the modulus, which is very hard to do for large numbers. In RSA, the private key is the modular multiplicative inverse of the exponent e modulo Euler's totient n. Euler's totient of n. Okay? Given two primes, p and q being these big numbers, and the exponent number e equals 65537, what is the private key d such as... What is the name for the symbol again? Is it is equivalent to, or what is the three line symbol in math? Let me know. People in math, people in chat, let me know, please. Equivalence, okay. So d is equivalent to e to the power of -1 mod Euler's totient of n. Equivalence, okay. So here are my notes for this particular lesson. Private keys. Okay, so in this lesson, we need to understand the concept of these RSA private keys and calculating private key values. So private key D, okay, and so in RSA, the private key is the modular multiplicative inverse of the exponent n modulo Euler's totient of n. Okay, I thought that was just red phi. Is it just red phi? Is it? Cipher, hello. As opposed to equals, which means equals. A is equivalent to B, equivalent to, but not equal to A. He doesn't know math or linguistics. Yeah, I mean, when you try to learn about cybersecurity concepts, you come across a lot of new stuff. Okay, we can express this as e to the power of -1 modulo phi of n. Phi of n. Let's do an example where e equals... So the way I try to understand this is I try to understand the math when the math is comprised of extremely simple numbers. So p equals 3 and q... p equals 3 and q equals 5 in this case. So we're solving for x, where 3x modulo 8 equals 1. Because this is how we figure it out. We start plugging in values for x, then multiply by 3 and divide by 8, and then compare the remainders to 1. So we arrive at the conclusion that x is 3, because 3 times 3, 9, modulo 8, gives us the result of 1. So that means in our example, 3 is the private key. In totality, given that n is 15, so p and q 3 and 5, and e equals 3, then the public key of n and e is 15 and 3, and the private key is n and d, which is 15 and 3. Okay, Dapel says, we'll make you a generalist yet. Yeah, I mean, you know, I'm sure Cypher isn't trying to be mean. Okay, for this challenge, we're asked to calculate the d value given these two numbers. So p equals this big number, q equals another big number, e is equal to the typical exponent, which is 65537. Okay, so we use a Python script over here. So RSA private exponent, we take in 3 parameters p, q, and e. So we got our p value, our q value, and our e value. So in the inside the function, phi equals p minus 1, q minus 1, like we did in the previous exercise. Yeah, no worries, no worries. I mean, I know Cypher. Cypher's been around for a while, so I hope that that Cypher is not trying to be, you know, super negative in chat. If it was like a new person who would wrote that kind of stuff as their first message, then it would be harder for me to tell that they are not trying to not trying to be super negative. Anyways, so we got a function over here. So phi equals p minus 1 times q minus 1. Then p is equal to the power of e to the minus 1 modulo phi. So modulo phi to the minus 1 power, and then return d. So this will give us, well, let's just try running the script over here. Euler's totient, sure. So private RSA dot pi, sure. Okay, when we run the script, we get this big number, which is the answer for this challenge. Tone is hard to judge in text. Yeah, it's hard to find tone in text, especially stuff like sarcasm. That's what emotes are for. Okay, so what we're gonna do here is we're gonna take a look at some other people's solutions. Ooh, where is it? Here. Okay, we've solved this challenge before. We'll take a look at the solutions. Okay, so this is a highly rated script over here. So the P, the Q, and the E, they plug these all in, and then phi equals, oh, this is exactly what I wrote for my script. I swear I haven't looked at these solution examples. Okay, and we'll take a look at another script as well. So this one's from the person who got the best score for the previous challenge. Oh, okay. So from crypto util number, import inverse. So they've got the P, the Q, and the E. So they can just inverse of E and phi, and then print D. The mathematics limit the amount of solutions you can have. Yeah, there's only so many solutions you can have. Okay, so this one is done. We'll move on to the next one. I really do think that public key crypto systems are very interesting. You know, RSA is also very interesting. The great thing about learning the RSA system is that, I mean, this sounds a bit weird. This sounds a bit lame, but you can solve a lot of cryptography challenges in CTF events if you know about how RSA works. Okay, so we're doing RSA decryption in this challenge. So I've encrypted a secret number for your eyes only using your public key parameters. So N is this and E is this. Using the private key that you found for these parameters in the previous challenge, decrypt this ciphertext. So the ciphertext is a big number. RSA used to be one of the most used crypto systems. Oh, I mean, I don't keep up with cryptography. What is the most used crypto system now? Okay, so what did I write for this challenge from my notes? So this is challenge number 5, RSA decryption. Okay, so the private key value we obtained from the previous challenge is this really big number. So if we use this script, so n equals, well, we've got our n, our d, and our c values. So c is the ciphertext, d is the private exponent, and n is the modulus. Okay, you see more of a variant of the elliptical curve algorithms currently. OW. I don't think I've heard of that one. Or maybe I have, but I don't remember. Okay, so the function is pretty simple. So our function here is m, the message, is equal to pow, that is c, raised to the d exponent, and then moduloed with the n value. And then we print decrypted integer m. So, and then we just run the function over here. Ow is a sound, not a word. Okay, okay. All right, so if we're to run this math, so this was, let's see, RSA decrypt. We have our big number values here, and then we run the script, and we get our decrypted integer leet 1337 1337. I mean, I'm pretty sure this is intentional. Okay, and let's see what some other people might have used to solve this challenge. Okay, so it looks like, yeah, there's only so many ways you can solve this. So here we've got n and c and then d. So these three values plug and play. Uses his private key nd to compute m, c to the power of d mod n. Okay, plain equals pow cd and n, print plain. This is pretty much exactly what I have, right? Yeah. It's only for doubly elite people to get. I guess that's the case. Okay, and we'll move on to the next thing. Okay, RSA signatures. I think this is where I got to before I stopped. How can you ensure that the person receiving your message knows you wrote it? You've been asked out on a date. You're asked out on a date and you want to send a message telling them that you love to go. However, a jealous lover isn't so happy about this. So, I mean, I don't know how... It's a funny scenario to think of, huh? When you send your message saying yes, your jealous lover intercepts the message and corrupts it, so now it says no. Okay, epistemic anarchist. Hello, nice to see you here. Elliptic curves are more common now. Most SSH will default to generating elliptic curve keys. You might have seen ED25519 in SSH keys. That's an elliptic curve. That's what Alice wanted to write me, of course. But epistemic anarchist, yeah, I mean, most of the time when I've been dealing with SSH private keys in CTF challenges, they're usually RSA keys. But you know what? I guess that it makes sense that in modern environments, we would be using a more secure crypto system. Yeah. We can protect against these attacks by cryptographically signing the message. Imagine you write a message M, you encrypt this message with your friend's public key, that is C equals, so C in this case is ciphertext. Ciphertext equals M to the power of E mod N. To sign this message, you calculate the hash of the message, so the hash of M, and encrypt this with your private key So S equals signature. So signature equals the hash of M to the power of D modulo N. Okay, RSA was the de facto algorithm for the last 40-ish years, and only in the last 10 years has this changed to EC algorithms. Randolph Stokes says, essentially we're looking to guarantee message integrity. Yeah, this is what signing is supposed to do. Your friend can decrypt the message by using the private key M equals C to the power of D modulo N, using your public key that they calculate, S, which is the signing key, equals the signature brought up to the power of E mod N. Now by computing the hash of M and comparing it to S, assert hash of M is equal to S, they can ensure that the message that you sent them is the message that they received. As long as your private key is safe, no one else could have signed this message. So what we need to do is we need to sign the flag crypto immutable messaging using your private key and the SHA-256 hash function. Okay, Epistemic Anarchist says the maths of RSA is easier, and there's more of those well-known failures in RSA, so more common in crypto challenges. I guess there are more vulnerabilities. There's more that can go wrong in RSA. I guess that's why we see it a lot more in those challenges. But Epistemic Anarchist, are you British by any chance? Because you say maths. Let me know if I successfully identified you. Okay. SysOS says 3 des, triple des is what RSA replaced, and triple des replaced DES, which is regular DES. Okay, so we also get a private key along with this challenge, so we can download it. Copy the link, and then download. wget. No, but AU. Oh, Australian, okay. Welcome to the stream. At least linguistically, okay. Close enough, I don't know. Alright, so we downloaded this key, and the key... essentially all the key has is the N value and the D value. So we need to incorporate these values into our script so that we can finish the challenge. So it says here that the output of the hash function needs to be converted into a number that can be used with RSA math. Remember the helpful bytes to long function that can be imported from crypto-util number. SysOS says it's the wayward colonials that dropped the S in maths. I guess so. All right, so let me talk about what I wrote for notes in this challenge first. So this is RSA signatures. So the concept in this challenge is digitally signing a message with RSA. Okay, sign the flag crypto immutable messaging using your private key and the SHA-256 hash function. So I've got a little script over here that uses hashlib and also crypto-util number. We're using specifically the bytes to long function over there. So the first the first part of this script is just extracting the values from the key file, because the key file is just a bunch of text with the N and the D values. So we've got values as a dictionary. So we open up the file as F, and then we scan over each line in F, each line in the file, and then we strip out all the white space. If the line doesn't have the equal sign, which means that the line doesn't have one of these values, then we skip that. Otherwise, we separate into key and value, line.split, on the equal sign, and we just get the first thing. So basically this extracts the N and the D values from the file so that we can use them later. Okay, we also have our flags, which is bytes, crypto immutable messaging. We need to hash this flag first, and then we need to encrypt it using our private key, so our N and our D values. So the integer, so the first thing we need to do is we need to find the value of the hash. So hash is SHA-256 function on the flag digest, the digest of that, which is a bunch of hexadecimal bytes. So the second thing is the integer equivalent of the hash, which is bytes to long on the hash. The last thing we calculate is the signature. So the signature is going to be pow on the integer of the hash raised to the power of d and modulated with the n value. So when we run the whole thing, we should be able to get the decimal representation of the signature. Okay, so we'll just copy this out. And because this is going to be done... Well, I don't have PyCryptodome installed on here, so I need to start up a virtual environment. So we can start up a virtual environment with this command, venv, run the virtual environment, and give it a source. And now we can install, what is it, crypto-util number. Or PyCryptodome. PyCryptodome, this one. Okay, because it's not installed by default, which is kind of a bummer. Anyways, we'll go in and we'll create this. We'll call it signing rsa.py. Okay, and then we'll save it out. And then we'll run the script. Okay, so we've got a few different things we're printing out here. So the flag value that we're going to be hashing is this right here. So the flag hash, after we've hashed it with SHA-256, is a bunch of hexadecimal bytes. Well, I mean these are bytes, but we're representing them in hexadecimal. So the signature is represented, the hexadecimal representation of the signature is this, and the decimal representation of the signature is this really big number over here, which is what we need to submit to the to CryptoHack to finish the challenge. Okay, and I'm pretty sure that the people over at CryptoHack, the students, they probably created like a much better solution for this, so let's take a look. Okay, so this is... You know, I've got the sneaking suspicion that they wrote pretty much something that's very similar to what I wrote. Oh, they're using a different module. So import hashlib. So m equals... So m is the message. M equals hashlib 256. Oh, okay. So they kind of skipped a step. So they take the bytes, crypto immutable messaging, and then they hash it with SHA-256 with the hashlib module over here. Okay, and then they've got the n value and the d value. So s, which is the signature, pow integer of m. Integer of m16. So this m16 is hexadecimal. So hexadecimal bytes, they're going to interpret it as the integer version raised to the power of d moduloed by n. Print hex of s. Print hex of s. Huh. What is this? Print hex of s. Hex of s, but starting from the second character. This is interesting. What I want to do, I'm gonna grab this code and I'm gonna give it a shake. It's just stripping the OX. Yeah. But I thought what we need to submit in this challenge is the decimal representation. Okay, so if you just run the script, you get hexadecimal representation. Can you also submit the hexadecimal representation and solve the challenge? Dude reads hex. Because when I solved the challenge, I submitted the decimal representation. I mean, I also have the hexadecimal representation here. Dude reads hex, don't hate. No hate here. Okay, let's move on to the next challenge. So this is stuff that I haven't solved myself yet. So just be patient with me because I'm not. This isn't necessarily going to go by very quick. So factoring. So far, we've been using the product of small primes for the modulus, but small primes aren't much good for RSA as they can be factorized using modern methods. What is a small prime? There was an RSA factoring challenge with cash prizes given to teams who could factorize RSA moduli. This gave insight to the public into how long various key sizes would remain safe. Computers get faster. SysOS says doing crypto by hand is hard. We get it. Yeah, it's I mean, I don't think of myself as a person that learns super quick either, so it might be a bit tedious. Computers get faster, algorithms get better, so in cryptography, it is always prudent to err on the side of caution. These days, using primes that are at least 1024 bits long is recommended. Multiplying two such 124-bit primes gives you a modulus that is 2048 bits large. RSA with 2048-bit modulus is called RSA 2048. Some say that to really remain future-proof, you should use RSA 4096 or even RSA 8192. However, there's a trade-off here. It takes longer to generate large prime numbers, plus modular exponentiations are particularly slower with a large modulus. So factorize the 150-bit number, this number, into its two constituent primes. Give the smaller one as your answer. Okay. Slide ruler or an abacus. Yeah, pulls out a lovely set of rainbow tables. Bone circuit. Hey, hello, nice to see you here. Okay, so what is the method you would do to split this up into two prime numbers? Okay, so factorize. Let me look it up. How to factorize prime numbers. Yay. Okay, I'll take a look at a math website. Okay, what is this? Prime factorization is a way of expressing the numbers as a product of its prime factors. A prime number is a number that has exactly two factors, one in the number itself. For example, if we take the number 30, we know that 30 equals 5 times 6, but 6 is not a prime number. The number 6 can be factorized as 2 times 3, where 2 and 3 are prime numbers. Therefore, the prime factorization of 30 equals 2 times 3 times 5, where all of those factors are prime numbers. Factorization with rainbow tables. We can factorize big numbers with rainbow tables. So factorizing it is harder the longer the prime number is. So let's learn about prime factorization with various mathematical problems, followed by solved examples and practice questions. So prime factorization is the process of writing a number as the product of two numbers. Prime numbers are the numbers that only have two factors, one in the number itself. So for example, 2, 3, 5, 7, 11, 13, 13, 17, 19 are prime numbers. Prime factorization of any number means to represent the number as a product of prime numbers. So for example, the prime factorization of 40 can be done in the following way. So 40, 20, 10, 5. So the prime factorization of 40 is 2, 2, 2, 2, 2, 2, 5, or 2, what is the word? Cubed. 2 cubed times 5. Okay, rainbow tables equals cheating or looking up pre-calculated factors. No worries, no worries. I mean, we might be doing a fair amount of quote-unquote cheating ourselves. So the method of breaking down a number into its prime numbers that help in forming the number when multiplied is called prime factorization. In other words, when a prime number is multiplied to obtain the original number, it is defined as the prime factorization of that number. Okay, so 36 is 2 squared times 3 squared. Okay, what are prime factors? Prime factors are numbers that are prime numbers that are multiplied to get the original number. So for example, 2 and 5 are the prime factors of 20. So let's think about this. So if we've got two prime numbers, so p and the q, so p equals 3 and q equals 5, and we know that these two numbers are multiplied together to get n, so n equals p times q, which is 15. So how would we figure out that 15 is... So is there like a formula to discover that 3 and 5 are the two numbers that were multiplied to get 15? Okay, Sick of the Mind says, not using methods that reduce compute cycles to execute complex procedures is cheating yourself. I mean, it's kind of like, what is the word? Password cracking. You can spend a lot of time using your CPU or your GPU to do password cracking, or you could also use the rainbow tables. So if you use the rainbow tables, you get other people's answers. You're using other people's answers that they calculated before. I mean, we know, in this case, that the two numbers that were used to arrive at the number 15 were 3 and 5. I mean, there are no other... 3 and 5 are two prime numbers that can arrive at 15. I don't think... Are there any other two numbers that can be multiplied to get 15? Bone Circus says, Brute and Rainbow are pre-password tables online. You can run RockU and others without a massive computer node. Yeah, I mean, It's like saying a screwdriver is cheating yourself. Cheating in the sense of doing the homework task here. I mean, yeah, we're trying to do this manually. One really great place that you can use for password cracking or hash cracking is CrackStation. So CrackStation's got a lot of good rainbow tables. Why are you making me count bicycles? Bicycles. Is that a bicycle? Is that a bicycle? Anyways, don't do this to me. It is in fact more efficient to use a known password list first before brute forcing. Yeah, I agree. Okay, so what they want us to do, factorize the 150-bit number into two constituent primes. Two constituent prime numbers. So if you've got a number that was arrived at by multiplying two prime numbers, can the factorization only be two prime numbers? I'm pretty sure that's the case, right? So if, I mean, let's do another example. Say that P is 7 and Q is 11, right? So in this case, N would be 77. And I'm pretty sure there's no other combination of two numbers that could multiply together to get the number 77 except for 7 and 11, right? There are no other possibilities. But then again, so what is the calculation that is done here? Kabuki Theater? What are we talking about? 1 in 77. Take care, Shanks. Thanks for the show. Bone Circuit, hey, don't worry. I mean, sorry. What was I going to say? Yeah, I mean, we're trying to learn the concepts. I think your comments were fine. They're fine. It's just that we're trying to figure out how to do this stuff manually. But yeah, hope to see you again sometime, Bone Circuit. Okay, so so back at 2 and 5 are the prime factors of 20. We know that the factors of a number are the numbers that are multiplied to get the original number. Okay. Prime factorization is similar to factoring a number, but it considers only prime numbers as its factors. Therefore, it can be said that factors that divide the original number completely and cannot be split into more factors is known as the prime factors of the given number. So we know that we're only dealing with prime factors when we're dealing with RSA. Okay, so there are various methods for the prime factorization of a number. The most common methods that are used for prime factorization, so you can use the factor tree method or the division method. I don't know either of these. Okay, in the factor tree method, the factors of a number are found, and then the numbers are further factorized until we reach the prime numbers. Let us understand that prime factorization of a number using the factor tree method with the following example. Okay, to get the prime factors of 850 using the factor tree method, place the number 850 at the top of the factor tree. Then write down the corresponding pair of factors as the branches of the tree. So here they're 25 and 32. How do we... So, okay, we know that 34 can arrive at 850. Really now? I mean, 25, sure. Factorize the composite factors that are found in step 2 and write down the prime factors as the next branches. So here 25 can be factorized into 5 and 5, and 34 can be factorized into 17 and 2. Repeat step 3 until we get the prime factors of all the composite factors. So we get the prime factors of 850 equals 2 times 5 squared times 17. So 850, 25, which is split up into 5 and 5, and then 17 and 2. So we multiply all these numbers together, 5 times 5 times 17 times 2, to arrive at the number 850. Okay, so Anarchist says, given that they point you to a prime factorization Python module, they might be expecting you to use that. I think the simplest algorithms might be a bit slow in Python for that big a number, and the harder the algorithm's a bit hard. Okay, so if we take a look at... So resources, how big an RSA key is considered secure today, and prime fac fork. Prime fac fork, what is this? Okay, this is a fork of the prime fac module. This software is okay, so this is a Python module, right? To directly install this repository, install git. Okay. So let's take a look at the README. Oh, this is the README itself. Okay, so this is Alright, so if we've got like a number that we want to split up into its prime factors, so 7 and 11. Well, we know for a fact that, well, we don't know for a fact, but we can pretty easily guess that 11 is one of the factors, and 7 is the other factor, because these are the two numbers that is divisible by in this case. And in this other case, we got 15, which is divisible by 5 and by 3. And that's all. I guess if you've got like really big prime numbers, it's a lot harder to look, to figure out what the two numbers might be at a glance, right? So what happens if we... So we've got a module here. So do we just... Prime factor fork uses GMPY2. Is there... Okay. So if we just search on the web, so Python prime factorization module. Okay, the most powerful and widely used external library for prime factorization in Python is SymPy. Okay, so that's it features a highly optimized N-theory module. So pip install SymPy. Is this installed by default? I don't know if it is. So we got our Python window here. Import SymPy. Nope, there's no SymPy here. Okay, so we can install it. So pip install SymPy. Okay, and then we should be able to import it. Import SymPy. Yep, okay, great. So what do we got? Okay, so factor int n returns a dictionary where the keys are the prime factors and the values are their exponents, their multiplicities. So factor print, factor int. So prime factors returns a sorted list containing only the unique prime factors. So what do we have over here? Factor int and prime factors. So we got the number 600 in this case. Okay, get factors with exponents returns print factor int number. So number is 600. So this is 2, it returns 2 to the power of 3, 3 to the power of 1, and 5 to the power of 2. Okay, and then get a list of unique prime factors. So returns 2, 3, and 5. So if we run these functions with with a number that only has one set of prime factors, then it's going to return the same thing, well, the same kind of thing for both of these functions, right? Okay, so let's just give this a try. So we run the Python shell, we import sympy, and then we set a number. So number equals 77, and then we run, what's the name of the sympy dot factor int on number. Okay, so it's 7 to the power of 1, and then 11 to the power of 1. And we're going to get something very similar if we run the prime factors function. So sympy prime factors on number. We get the unique factors, which are 7 and 11. Okay, so if we set our number to the one in the exercise, which is this really big number. Okay, factorize the 150-bit number into its two constituent primes. Give the smaller one as your answer. And then we run prime factors on number again. So it's going to take a while to calculate, I guess. So I wonder what the function actually does. The other thing that I'd like to know is there like is there a method of solving this in Python that doesn't involve importing? Well, I mean, there has to be a method of solving this in Python without importing some module, right? But is it easy to do, or is it pretty involved? Uh-oh, this is taking a long time to come back. Anyways, well, so the prime fact fork, you can do trivial division for small numbers. It would be slow. Yeah, I guess it would be slower if you're not using a dedicated module. And we got the numbers. So how many digits are these? I can't tell at a glance which one is smaller. This one is smaller, right? Okay, I think it would divide by prime numbers until it returns an integer. That makes sense. Okay, so let's submit this number. I'm actually interested to see incorrect flag. Okay, so the smaller number is this one. Okay, that was the correct answer. That's the trial division method. All right, let's see if I can put on some new music. Just a second. Which soundtrack do we want to play? How about some FTL? Anarchist says, I'm guessing SymPy is actually using more complicated methods which speed things up. I mean, maybe. Okay, so now that we've solved this, I want to take a look at some of these solutions. Okay. So just use factordb.com. Just use factordb.com. Wow, that's a choice. Sure. Okay, so I mean this is the rainbow table answer that people were talking about earlier, right? It's probably C under the hood, maybe. I mean lots of Okay, so why did everybody upvote this? I thought we were supposed to avoid like simple. I mean this is a super simple answer. Okay, let's give it a try. So these are Fanto, hello, nice to see you. It has been a while. All right, let's. So this is like the rainbow. This is the rainbow table method, right? Okay, they want us to factorize a big number. So we supply this. Okay, so 45 digits. 45 digits, and then we've got 23 digits and 23 digits. Oh, you know what? This is very this is very convenient because I can tell immediately which one is a smaller number. This is a smaller number because they're both 23 digits long. Okay, Anarchist says, at least for large numbers, yeah, probably optimized libraries. SymPy is full of computational algebra and symbolic math systems. Randolph Stokes says, there's more to learn by doing it yourself than pulling up a website. I mean, that's true, but I mean, if you want to get the job done, I guess what you want to do is you want to have multiple methods of getting the job done. It's always better to have at least 2 methods of solving the same problem, just in case one of the methods is not available to you. Okay, let me try to do a little write-up for this exercise. So this is lesson number 7. Prime factorization. So we need to record the URL where we can find the thing, and then the concept, and then the method of solve. Oh, it's just called factoring. Okay. All right, let's go back. Okay, so this is the URL here. The concept is calculating prime factors. And I guess we can record the stuff covered in the lesson as well. So I'll just record this over in my write-up document. What is a small prime, huh? Okay, factorize the 150-bit number into its 2 constituent primes. Give the smaller one as your answer. Sure. Okay, so we'll provide at least 2 methods of getting this done. So the first method we could use is a website that has pre-calculated factors, and that is this one over here, which we'll record. It's called factordb.com. The other method involves using a Python script using the Python script with the SymPy module. So that is Python I mean, it's very so from SymPy import something something, right? Whoops. From SymPy import, what is the name of the thing? Prime factors. So we just, well, define the number over here. So number equals this thing. Feel like you keep calling me teacher senpai. Well, no, not exactly, but also use. Use? Sorry, what were we talking about? Did I make a... The first method we could use is a website that has pre-calculated factors. The other method involves using a Python script with the SymPy module. Okay, number equals this. And then we just run prime factors, or print prime factors. Print prime factors on number. Okay, and before we finish this out, I want to see if anybody has any other Python methods of solving this challenge. So no dev 96. So Python M. Thanks for updating the project elliptical. Okay. So Python M prime fac. Python M. I'm pretty sure we can't run this from the command line, can we? Well, let's give it a try. Yeah, there's no module named primefac. Okay, so if we installed primefac, only one way to know. Okay, that's using that Python module that they linked. Yeah. So the Python module is here. To install directly from the repository, pip install this thing. Okay, we've got a command. We'll give it a try. And it might be faster than... Wow, that was really fast. That was a lot faster than the SymPy one. No, that's yeah, that's great. Okay, so all right, so I guess we'll provide a third method of solving the challenge. Where are we? So we can also use the recommended module for doing the prime factorization. Okay, it uses, the Python module uses factordb. Oh, okay. So it's like a wrapper? So it's like a wrapper that contacts the FactorDB website? That's interesting. So I guess this one doesn't actually crunch numbers. This one just like does a lookup. Okay, it does other methods too, but it uses FactorDB for big primes. That's like cheating with extra steps. Kind of. Okay, so it's like pip install this thing, right? And then run the module command. Okay, and we can move on to the next thing. I was sitting here wondering how it calculated it so fast. I mean, I guess everybody's got the same idea. Just look up like a rainbow table. Okay, let's do the next challenge. So that was factorization. And the next challenge is monoprime. Why is everybody obsessed with multiplying 2 primes for RSA? Why not just use 1? Huh. This seems like a CTF challenge. So output files, output.txt. Why do we need in RSA the modulus to be the product of 2 primes? I mean, I'm not a math person. I don't know immediately what this is, but it seems like... Okay, so SymPy says, describes the algorithm SymPy uses. Oh, okay. All right, so this one's called monoprime. Let's start the write-up. Hold on, what number is this? So this is number 8. Called monoprime. Christian Rink says, just tuned in, reading SymPy and my heart goes off. Z3 is also nice. I don't know what Z3 is. Let me know. And Christian Rink, welcome to the stream. Nice to see you here. Okay, so the concept for this challenge is using a single prime for the n value. Single prime. For the n modulus in RSA. So the URL for this challenge is over here. And I'm pretty sure everybody can view this, even if they're logged in case they wanted to take a look. Okay, so why is everybody obsessed with multiplying 2 primes for RSA, and why not use 1? Okay, the challenge includes 2 files for us to download. So the 2 files are output.txt so we'll wget this. So what is output.txt? So we got an N and we got an E. And we have a CT value. So CT, I'm assuming, is ciphertext, E is the exponent, and N is the modulus. Okay, and let's see. The output There's not two files for us to download, there's only one. Includes a file for us to download called output.txt. Christian Rink says, Z3 is an SMT solver by MS. Lots of fun, can be used to solve logical problems. Awesome, awesome. Okay, so we're given, so this file gives us the following values. Okay, so it's N, E, and CT. So, so C is ciphertext, E is the exponent value, and N is the modulus. I don't know. I don't know exactly how we would take advantage of the fact that N is only a singular number. Oh, you know what? So in one of the previous challenges, we talked about the Euler's totient. So the Euler's totient was this function over here. So phi from P and Q. So P and Q return P minus 1 times Q minus 1. So P minus 1 times Q minus 1. It has to be, the way we take advantage of this has to be it has to be somewhat related to this, but I'm not exactly sure. Okay, let's do a little bit of reading. So why do we need RSA, the modulus, to be a product of two primes? Let's do a bit of reading. Oh, this is an old school looking website. Okay. So I roughly understand how the RSA algorithm works. However, I don't understand why we need the n, which we use as a modulus, to be pq for some large primes p and q. I vaguely know it has something to do with factorization, but I'm kind of lost. So hypothetical questions. What would happen if the n was not pq, but just a big prime? What if n would be some random composite that's easy to factor, and the other parts of RSA remain the same? Okay, what are the answers? So RSA would still work with such an n, but isn't secure for n that is easily factored. If you know the factorization of n, which is trivial for prime n's, you can calculate the private key. You can calculate the private key from the public key. This totally breaks the desired security properties of RSA. The essential equation for RSA is message phi of n plus 1 equals m. Mod n for all m. That works for all n, but only for some n it is hard to calculate. So phi of n. When we're using RSA, we require phi of n to be hard to calculate. Since once we know phi of n, you can get d from e by solving e times d equals 1. E times d equals 1 mod phi of n, using the extended Euclidean algorithm, just like what you would do when legitimately creating the key pair. If n has more than two factors, but at least two of those are large and hard to guess, it's still secure. But almost nobody uses this RSA variation. Okay. So how do we do this attack? if you know the factorization of n. The essential equation for RSA is that, So we have the ciphertext, we got the E value, we have the N value. We had to find some way to abuse the N to create a private key. Let's go over what we know. Ghost Strats, hello, nice to see you here. Hope you're having a good day. So when we took a look at RSA decryption, we were given the N value and the E value. So use the private key that you found for those parameters in the previous challenge to decrypt the ciphertext. So the private key that we got was from here, and we used this kind of script over here to decrypt the ciphertext. Okay. Let's copy this. Okay, yeah, doing okay, learning about new stuff. So I'm not a person who is very good at math, but I'm trying to learn math in order to learn about cryptography, which has a lot of math. Monoprime.py. Okay, so we got the N, the D, and the C. Just for... Just for the sake of speed, I'll just copy this over. So our new values are n equals this really big number. And let's get rid of this. The D, we don't know what the D is, but we know what the ciphertext is. Okay, Ghost Rats, I love this stuff. Never got to this level, though. Never got to this level. Oh, you mean you're talking about CryptoHack? So the platform I'm using to learn about public key cryptography is CryptoHack. If you're interested in learning about cryptography, it's a very, very good platform. So we have our N, we have our E, and we've got our CT. So the decryption is going to be CT taken to the elevated to the power of D. D is, let's see. The D value is the private key, right? So one more time, we calculate the D value by getting the private key D is used to decrypt ciphertext created with the corresponding public key. Maths for those that never got their freedom. I guess so, yeah. Okay, in RSA, the private key is the modular multiplicative inverse of the exponent, E, modulo phi of n, Euler's totient of n. So the Euler's totient of n so we want to For this challenge, we're asked to calculate the D value given the P and the Q and the E. The P, the Q, and the E. So if we know the P and the Q, then phi is equal to P minus 1 times Q minus 1. But we know that in this case, it's only one number. So if it's only one number, it's just phi equals the private key exponent is... Okay. Anarchist says you've got to calculate D from that N. D from that N, yeah. So D is supposed to be tau of E minus 1 and then phi. So phi is the Euler's totient. Sorry, not Euler. The Euler's totient. The Euler's totient. Okay, but what if there's only one number? If there's only one number, then it's just... it's not multiplied. So it's just... is it just... is phi just something minus 1? Okay, the Reddit post gave you the math you need for the singular prime. Okay, let's take a look. Let's take another look at the what is it? This thing. Just a second, I need to close out some of these windows. Okay, the essential equation for RSA is that M when using RSA we require phi of n to be hard to calculate. Since once you know phi of n, you can get D from E by solving E times D equals 1 mod phi of n using the extended Euclidean algorithm. If n has more than 2 factors, so more than 2 factors is not what we're talking about. If you know the factorization of n, which is trivial for prime n's, so is it just the prime itself in 1? So if we're... that would be my guess? Okay, so we're looking at... so RSA private exponent is phi equals... I mean, the P and the Q, if we go by this, then phi equals the really big number times 0, because 1 minus 1 is 0. And that doesn't make any sense. That doesn't multiply. No, I mean, we just get 0. Phi equals 0. So we would get tau of E to the minus 1 modulus 0, or modulo 0. So P being the really big number and Q being 1. Searching Euler's totient gives, Euler's totient gives other formulas. Okay, so I think I saw at least 2 different methods. For any positive integer n, the totient is calculated as phi n equals n times, what is that? What is that symbol? Apparently for prime number p, it's just p minus 1. For prime number p, it's just p minus 1. Really? Huh. Wait. Click show more. For a prime number. You're right, anarchist. Wow, okay. So for a prime number p, phi of p equals p minus 1. So if we go into here, and we're trying to calculate, oops. Okay, we got our P, our Q, RSA private exponent. We have to calculate the private exponent first. So we'll do that over here. So RSA private exponent involves P, Q, and E. So we have phi equals n minus 1. Phi equals n minus 1. So in this case, private exponent, RSA private exponent for 1. This takes in just n. This takes in n, n and e. So phi equals n minus 1. And then d is equal to pow of e minus 1 and then phi, and phi is just that really big number, n minus 1. Return d. So we can calculate d down here. D equals RSA private for 1, n and e, like this. Now we need to get e for the RSA decryption. So we have the e value up here. And then we've got CT, so to decrypt it, m equals pow of CT to the power of d, and n. And then the decrypted message is this this big number. Are they looking for the number? So in the challenge, they're looking for a flag. So crypto flag, so we probably need to convert whatever integer we have. So decrypted integer is this, but we can also print out decrypted hex, so hexadecimal, which is the hex of M. And I guess the other thing we could do, we could convert the hexadecimal into ASCII characters after. But let's just try and see if this script works first. So Python, what do we call it? Monoprime. Okay. Perhaps you forgot. Oh, we forgot to invite. We gotta. We need to put a comma here. Okay, we've got our decrypted hex, and we got our decrypted integer, and we need to get a message from this. So I'm pretty sure if we plug this into hex to ASCII, we should be able to get the answer. So hex to string. Okay, and then convert. Nope. That's not it. Okay, so I can go for another 15 minutes, but then after that I really need to think about getting going, because I've got an event to go to tonight after the stream is over. Just a second, everybody. Okay, how do they convert text to a number to encrypt it for? I mean, did they? So it says enter the flag here. It should be crypto flag. So it's hexadecimal convert to ASCII text, but this doesn't convert to ASCII text. There's a bunch of non-printable hex characters in here. Okay, so maybe I should just ask what the I should ask how they do it normally over here. Okay, I'm decrypting an RSA encrypted message. But I only have decimal and hexadecimal values. I want to decrypt to ASCII characters. What was the RSA? Yeah, Okay, and let's get the monoprime script here. And thank you very much to April for redeeming the Budweiser frogs. Thank you. Oh, it's thinking. Okay, your decryption formula is the problem. Oh, your decryption formula is the problem. So d equals e to the -1 mod n -1 is only valid when n is prime. When n is prime, which RSA moduli are not. For this ciphertext, the straightforward pow ct dn using that shortcut does not produce a value, but the result does not. Using that shortcut does produce a value, but that result does not cleanly decode as ASCII with a direct hex to bytes conversion. Okay, the computed plain text integer corresponds to this hex value here. That hex string is not valid ASCII text as is, and it also indicates that the decrypted integer is much larger than a normal short message block would be. Okay, so, what's... Go Strats, gotta go, good luck, and well, thank you very much, Go Strats, and I hope to see you again next time. Okay, recover the actual RSA plaintext properly if this is a factorization or CTF cell problem. Okay, so, maybe I'm not doing this correct. So we have the definite n value, the definite e value, and the definite CT value with this, which is the ciphertext we need to decrypt. So we get the d value for from running this function. So phi equals n minus 1. And then we derive the d value from that. Didn't you do the hex to string conversion in the RSA decryption challenge we did previously? We did we? I don't think we did. I don't think we've decrypted anything to ASCII characters. We didn't decrypt hex to string, we just took the raw integer value. We did, oh no, we did do, what was it? We did convert hexadecimal to wait, what was it called again? Like bytes to long, or long to bytes? Hold on. Yeah, the output of the hash function needs to be converted into a number so that can be used with RSA math, and then we used bytes to long. So we converted bytes into decimal numbers. Maybe long to bytes would work. Long to bytes. Okay, so I mean, and we're also doing crypto util number. Long to bytes. Hold on, let me look that up. Okay, so apparently, to convert a large integer to bytes in Python, you can use the native int to bytes method, or the popular crypto util number long to bytes utility, okay? Calculate the exact number of bytes needed. PyCryptodone method, common in CTFs and cryptography. So you would do, so the big number converted into byte data, we get hello. So from crypto util number import long to bytes. Sure. Let's give it a try. Okay, so decrypted hex, decrypted integer, and we've got decrypted bytes. And we run long to bytes on M. Yeah. Okay, let's give it a shot. And you know what? I also want to put a... let's just do it like this. Okay, so we got our decrypted bytes. So the bytes are different from the hexadecimal, but they still don't look like printable ASCII values. We have printable ASCII values in here, but yeah, I'm doing something wrong. Okay, I'm running out of time. I'm just gonna ask for some help. Okay, we're doing a CTF where we need to decrypt a message based on a flawed RSA implementation, where the N is comprised of a single large prime number. Okay, that setup is exploitable because RSA normally requires n equals PQ, but here n is a single prime. So phi of n equals n minus 1, and the private exponent is d, which is equivalent to e to the power of minus 1 mod n minus 1. How to decrypt? Use the same structure you already wrote, but interpret the results as bytes after decryption. Okay? So convert integer to bytes. Message equals m dot 2 bytes m bit length. So here's what we didn't have before. So we didn't know the length of the bit of the bits. So in this case, we need to interpret each one as 8 bits. Okay, so we'll grab this, and then we will mod n minus 1. Anyways, let's go back in. Okay, in this case, we're not using long to bytes, so we don't need this. So d is equal to pow of e minus 1 and then n minus 1, which we have up here. The message is equal to pow of ctd, which was calculated here, and n. Convert integer to bytes. Message equals m dot 2 bytes. M dot bit length. Bit length is going to be set to 7 because this is ASCII encoding. And then divide by 8 because divide by 8 because this is 8-bit encoding in big endian order. Print the message, and then print decoded from ASCII, replace with errors. Replace any errors. This is still this is still incomprehensible. Huh. That's interesting. What am I doing wrong? Okay, if the decrypted bytes don't look ASCII, the plaintext may be padded, encoded in hex or base64, or in a binary flag container rather than plain hex. If pow e minus 1 n minus 1 fails, then GCE, greatest common denominator. So the key is invalid for this instruction. So in these prime modulus RSA challenges, the core trick is usually not factorization. It's recognizing that the modulus is prime and that phi of n equals n minus 1 to recover the private exponent directly. Yeah. I mean, the other thing is that this might not be it might not be big endian order. So if it's not big endian order, instead it's little Endian order. See if that changes anything. It doesn't really change anything. Never mind. Okay, I think the previous solution might have just messed up the E. The previous solution might have messed up the E calculation. I think that the long to bytes was probably fine. Okay, so if we're let's go back in. The D calculation, right? So the D calculation. We'll go back in. We'll import the is it long to bytes? This one. Whoops, we don't want to import it here. We want to import it up here. Print long to bytes on M. Actually, the previous script kind of outputted the same stuff. I think it outputted the same stuff as this one did. Okay, I have to go to an event, so I've got to unfortunately I'm gonna have to call it here. But we're gonna be streaming next week. So this was week 26, and we're gonna be streaming up until week 27. And the schedule is over here. Okay, so what we're going to be doing, we're going to be doing puzzle games, we're going to be doing web app challenges, we're going to be doing more network hacking stuff. We're going to be taking a look, like a deeper dive over at SQL injection, over at Portswigger, on the Wednesday stream. On the Friday stream, we're going to be taking a look at a PicoCTF course on AI foundations. I guess it's not called PicoCTF, it's called Scilab now. And if you want to take a look at the stuff that we're going to be looking at, AI Foundations 1 is the name of the event. Okay, it was an amazing stream. Thank you very much, SOS. Crypto is tricky to learn. Yeah, it certainly is, especially if you're not good at math. But yeah, this event is going on right now. They've got a new course over at Scilab, which teaches about AI foundations, something that I want to learn about. So everybody, please stay tuned for. Sorry, that's not stay tuned. Please look forward to the streams next week, and they're going to be on July 1st and July 3rd. And I hope everybody has a good weekend. I hope you all stay very, very cool. And in the meantime, let's see if we can find some people to write into over on Twitch from the InfoSec Streams channel. I'm the only one at the InfoSec Stream channel. Great. Let's find somebody from some cool people on Twitch. It's tricky even when you're good at maths. Who do we have? Moohoodles. Moohoodles is well, all what? No. MSec. MSec is a cybersecurity professional. Huh. How come his stream wasn't on? Oh, he's playing Minecraft right now. Dirty Celsius right now. Cool, yeah. Hope you all stay cool, stay safe. And you know what? We haven't raided into MSec. This stream is sponsored by Minecraft. Really? Is it? Yeah, I think you're probably going to have a better time over at Moohoodles, because she talks about science stuff. Hold on. Let me pull up her stream. Okay, she's currently talking about astrobiology and space news. And she's very, very animated right now. Okay, let's go ahead and start the raid. Whoops, it's supposed to be /raid. Okay, everybody, when you arrive at Moohiddle's channel, if you could give this message right here, OSFrog, Hip Hop Hack, OSFrog, I would really appreciate it. Alright, everybody, HackerFrogs, we're going to be back on Wednesday, ready to raid in 5, 4, 3, 2, 1. Happy weekend, everybody.